Hello, welcome back to my recorded classes. This recorded video, we are discussing some questions from module number 1 and module number 2. It is like a worksheet from the topic 1.3 to 2.6. That means from first modules starting from 1.3 and second module up to 2.6. So from linear algebra, we have one worksheet here. We will do one by one. So let's start the topic here. Actually, module 1, as you know, we have 1.1 to 1.8. 1.1 system of linear equations and 1.2 is matrices. These two are some basic sections. Okay. And from 1.3 onwards, we are started the original topics. 1.3 solving system of linear equations. 1.4 is vector spaces. Then linear independence, basis, dimension, rank, then linear mapping and affine spaces. Okay, so we will start with the first section 1.3. Let's start the ideas. So throughout this worksheet, I am using this calculator FX991 ES plus. Okay, you can also try with this calculator for easy calculations. Okay, so let's start the first idea 1.3 section. Solving system of linear equations. So this section, what are the main ideas we are studied? Okay, we will discuss one by one in the worksheet. So first one, how to find the rank of a matrix. How to find the rank of the matrix. So example here, find the rank of the matrix A equal to 1, 2, 1, minus 3, minus 1, 7, 2, 1 and minus 4. So we know rank means number of non-zero rows after changing to the canonical form, okay, or echelon form reduction. After that, how many non-zero rows are there or how many number of pivots are there, we can calculate. Here in the throughout in this worksheet, I am using row reduced echelon form or canonical form. Okay, so let's start with this question. Just worksheet only. The theory or ideas I am not discussing here. Just some doing from each section one or two questions, concentrating. So this question, find the rank of the matrix A equal to this matrix. Okay. So we will start the transformation, row transformation and changing the matrix into the canonical form or row reduced echelon form. Okay, so let's start the matrix here. A equal to, our original matrix is 1, 2, 1, minus 3, minus 1, 7 and 2, 1, minus 4. Now for changing to the row reduced echelon form, okay, first we need to check the first number. This number should be 1 here, should be 1. So already here it is 1. This number we are calling the pivot number. It is coming on the first row. So what is the first step we need to do is the down numbers all should be 0. So this number and this number both we need to change into zeros. So what are the rows we need to change? Actually we need to change the second row and we need to change the third row, correct? So R2 means we can study like this, R2 plus is default. Now opposite of the number minus 3. Minus 3 opposite is plus 3. Multiply pivot number coming row. That is the first row. 3 R1 plus R2 gives new R2. And same way the third row we are changing. Now third row, how we are transforming that one? R3 plus is default. Opposite of the number 2. That is minus 2. Multiply pivot number coming row is first row. Actually this rank of the matrix calculation, this section very detailed we are taken before, how we are using calculator and how can we change a matrix into the row reduced echelon form or canonical form. So here I am doing little fastly here. So equivalently matrix, when we are applying this transformation, these two transformation. So first row there is no change here. So 1, 2 and 1. Now second and third row we are changing by using this transformation. So as I told you before videos, before recorded classes, 3R1 plus R2, correct? 3R1 plus R2, that is the new R2. So when you are using this calculator, above I mentioned one calculator in the previous slide. So 3 multiply, instead of R1 we are typing as X in calculator, instead of R2 we are typing Y as the calculator. After that, we are using the calculation button, calc button. It is available in our calculator, calc button. Once calc button it is pressing time, calculator will ask what is your x number. X number means the first row number. What are the first row number actually? 1, 2 and 1, correct? What is the second row number actually? -3, -1 and 7. So once you press the calc button, immediately calculator will ask what is your x number. So x number means the first row number. So what is the first row number here? It is 3, correct? This is the R1. First row number is 1. Okay, then press equal to. After that, okay, calculator immediately it will ask what is your y number. Y number means the second row number, correct? Second row number here -3. So press -3. After that press equal to. So immediately calculator you will get the answer. So equal to 0. So we can update here that number 0 here. Now same way again press the calc button. Okay, again press the calc button. So immediately calculator will ask what is your x number. X number is 2 and press equal to. Immediately calculator will ask what is your y number. That is 1. Sorry, y number is -1. Okay, my y number is -1. So press equal to. So you will get the answer equal to 5. Then again press the calc button, x number, that is row number 1, first row number 1, then y equal to y number, it is 7. So once you press equal to, you will get the number here 10. Now similar way we are calculating the second operation, -2 R1 plus R3 gives new R3. Okay, so now you can press the calc button here. See, -2 times R1 plus R3 gives new R3, correct? So you can type this one in your calculator, -2 instead of R1 plus X plus instead of R3 you can type Y. X and Y we are getting if we are using alpha button. Okay, alpha button in this calculator, you can see here one alpha button is there. Once you press alpha button and this X button, okay, or Y button is here. Okay, you can type that equation in your calculator. So here I am doing -2 R1 plus R3. So R1 means the X, R3 means Y. That means R1 means first row number, correct? So X means the first row number, that is 1, 2, 1. And Y means this third row number. Okay, third row numbers, what are the third numbers? 2, 1 and -4. 2, 1 and -4. So you can press the calc button. Okay, once it is pressing, calculator will ask what is your x number. So you can type what is your x number. Here x number is, first row number is 1. Then press equal to. So calculator will ask what is your y number. Y number is the third row number, that is 2. Press equal to. So you will get the number in calculator, it is 0. Correct? So the same operation you can continue. Press the calc button. X number 2, y number 1. Okay, you will get -3. Again x number 1, y number -4. Okay, after pressing calc button you will get -6. Okay, so these two row transformation we calculated by using the calculator, using the calc button. So immediately we will get this matrix. Okay, now again what happened? So the first number is 1 here, and down numbers already we changed into 0 numbers. Okay, here it is 0, here also it is 0. Now you can check the next one. The diagonal number here, the second row first non-zero number should be 1 here. So this number should be 1. So what we need to do, that row number 2 completely divide by the same number, that is 5, gives new second row. Okay, second row completely we divide by the same number, so that we are getting the new second row. So equivalently what will be that matrix? First row there is no change, so 1, 2 and 1. Second row, all the number we divided by 5. 0 divided by 5, that is 0. 5 divided by 5, that is 1. 10 divided by 2, that is 2. Correct? Now third row same, that is 0, -3 and -6. Now after that, this is the pivot number now, the one number, second row. It is coming on the second row. Now pivot number, down number and top number should be 0 here. So we need to change number 2 and -3, that row, first row and third row. So first row R1 we need to change here. So R1 plus is default. opposite of 2 number, okay, that is minus 2, multiply pivot number coming on second row, minus 2 R2 plus R1 gives R1. Now same way we need to change the third row. So R3 plus is default, opposite of minus 3, that is plus 3, multiply pivot number coming on the second row, so R2. Now as I told you just before, you can use your calculator using the calc button. So I am writing the changed matrix here, okay. So it is equal to, okay, you will get the number, first row become 1 0 and minus 3, second row becomes, second row we are not changing anything, 0 1 and 2, third row becomes 0 0 and 0, that row completely it is changed into 0 here. So now the matrix is, it is in canonical form or row reduced echelon form, because the first number is 1, the down numbers are 0, then next row first non-zero number is 1, okay, that is, and the top number down numbers are zeros, next number fully it is 0 next row. So this is the canonical form or row reduced echelon form. Now after changing into row reduced echelon form, you can see rank of the matrix, that is the question, correct. So rank of A equal to what was studied actually, number of non-zero rows, correct, number of non-zero row it will not count, number of non-zero rows we are taking. So how many non-zero rows are there? It is equal to 2, correct, because the last row only we have the 0 row, last row it will not count, the first row non-zero row, second row also non-zero row, but third row is 0 row. So number of non-zero row equal to rows equal to 2. So that is the rank of the matrix. I hope you clear this question, okay. Now we will go to the next idea from this section, that is general solution of a system of linear equation. How to calculate the general solution of a system of linear equation. So here you can see this flow chart, so that easily you can understood, okay. So linear system we have two type, one is homogeneous, one is non-homogeneous system. Homogeneous system always it is consistent, okay, because zero solution always it will be there, so always it will be consistent. Homogeneous system means it is of the form Ax equal to 0, right side it should be 0, completely 0, full 0, right side of the equation fully 0 means homogeneous equation. Homogeneous equation it is always consistent, no need to check the consistency condition, okay. But only two case, either it have trivial solution or non-trivial solution. Trivial solution means zero solution, only zero solution. Only zero solution means x equal to 0, y equal to 0, z equal to 0, like that. So zero solution, when it will come, rank of A equal to number of variables or number of unknowns. We know already, we discussed how to check the rank of a matrix. So rank of A equal to number of unknowns means, or number of variables means, that a system having trivial solution or zero solution, only zero solution. Now non-zero solution or non-trivial solution, when it is coming, if non-zero solution happening, it have infinite number of solutions, okay. So when it will be that one, rank of A less than number of unknowns, rank of A less than number of variables, okay. So that case the system having, homogeneous system having infinite number of solutions will be there, non-zero solutions other than zero solutions, okay. Now second category, it is non-homogeneous solution. Non-homogeneous solution means it is of the form Ax equal to B. That means right side of the system we have some numbers like 1 2 3 like that, other than 0. Sometime one number will be 0, but not all 0, some number will be non-zeros also. So non-homogeneous system of equation. Now if you are getting a non-homogeneous system of equation, always we need to check it is consistent or not, okay. So how we are checking consistent or not? Consistent means that system having a solution, correct. So when it is consistent, if rank of AB equal to, we just calculate the rank of the augmented matrix AB, A and B together, and if it is same as rank of A, that system is consistent. Now if rank of AB greater than rank of A means that system is inconsistent, there is no solution in this case, okay. Rank of A equal to equal to rank of AB means we have consistent. Now in consistent there are two cases, one is a unique solution, only one solution, and second one infinite number of solutions, correct? So when it will have unique solution, rank of A equal to number of variables. Rank of A equal to number of variables means we have unique solution, and rank of A less than number of unknowns means we have infinite number of solutions. Okay, we have infinite number of solutions. Same like here, see here it is zero solution, but here it is unique solution. Unique solution means only one solution, like x equal to 1, y equal to 1, like z equal to 2, like that numbers. Okay, unique solution. Now infinite number of solution means rank of A less than n. Here also same that one, rank of A less than n, infinite number of solution in homogeneous case also. So let's do some practice question here, one practice question here. For example, find the general solution or all the solution to the system of equations minus y plus 2z equal to 1, x minus 2y plus z equal to minus 1, x minus 4y plus 5z equal to 1. Find the general solution. Okay, find the general solution of the system of equation. Now here in this question, when we are considering the right side numbers, you can see 1, minus 1 and 1, correct? So it is a non-homogeneous solution, non-homogeneous system. Non-homogeneous system means right side we have some numbers, correct? So this is a non-homogeneous system of equation. So as I told you just before, if we have a non-homogeneous system of equations, okay, what we are doing first? Non-homogeneous means first we need to check consistent or not. We need to check rank of A, B and rank of A. If both are same, it is consistent. Otherwise, it is not consistent, correct? So we will go first, we need to write A, B matrix. Okay, A and B matrix we need to write together, augmented matrix A and B. So we can write here, for example, AB means just write the behind number in the first equation. There is no x term, so 0. Y behind number is minus 1. Z behind number is 2. And now we are writing B numbers. B numbers means right side number, that is 1. Okay, like this. Now the second equation, x behind number is 1. Y behind number minus 2. Z behind number is 1. Right side number is minus 1. Third equation, x1, y behind number minus 4, z behind number 5 and right side number is 1, correct? Now we are starting the row transformation. Using the row transformation, we need to change the matrix into the canonical form. So here when we are changing to the matrix, here the first number is 0, but here this position first number should be 1 here, correct? Pivot number first starting non-zero number should be 1 here. So what I am doing here, the first row and second row I am interchanging, because in the second row here you can see the number, correct? 1 is here. So we need to interchange these two rows, or we can interchange with the third row also, no problem. Okay, first row or first row with the second row, or first row with the third row. That is up to you, up to the questions. Okay, because you know both are 1 here. We need to get to first number should be 1. So here I am interchanging the first row and third row for convenience. Second row also you can interchange. So equivalently the matrix, it becomes the matrix. Okay, third row become first row. Third row is 1, minus 4, 5 and 1. Second row same, 1, minus 2, 1 and minus 1. Third row become the first row. First row become the third row now. 0, minus 1, 2 and 1. Okay, I hope you clear this step. You can interchange the second row also, there is no problem. Okay, here I am changing the 0 to the last. That's why I interchanged with the third row. Now, the first number here 1 here now. So this is the pivot number now. Pivot number coming on the first row here. Now pivot number down numbers we need to change into zeros here. So here it should be 0. Here already it is 0, so no problem. So this number we need to change into 0. So this number means we need to change the second row, correct? R2. So what we are doing, R2 plus is default. Now opposite of the number 1, that is minus 1. Multiply pivot number coming which row? That is the first row. So minus 1 multiply R1 plus R2 gives new R2. So equivalently, what is the matrix we are getting? Matrix, the first row there is no change. 1, minus 4, 5 and last number is 1 here. Second row completely we need to change by using that transformation. Already we cleared that transformation, how we are applying the previous questions, and you have one separated recorded class from 1.3 that I am explained detailed there how to change, how to do that calculation easily. So here I am doing the second row, that row transformation. So we will get the matrix 0, 2, minus 4 and minus 2. After the row transformation, these are the numbers, you can check by calculator. And the third row there is no change, 0, minus 1, 2 and 1. Okay, I hope it is clear in this step. So first number is 1 here, down numbers we changed it into 0. Now the second row, first non-zero number should be 1. So here I need to change this number into 1 here, correct? So we need to divide the second row completely by 2. We will get a new second row, correct? New R2. So equivalently the matrix, first row same, that is 1, minus 4, 5 and 1. Okay, second row complete number we divided by 2. 0 divided by 2, that is 0. 2 divided by 2, that is 1. Minus 4 divided by 2, that is minus 2. And the minus 2 divided by 2, that is minus 1. Third row there is no change, 0, minus 1, 2 and 1. Now what is the next operation we need to do? Now this number is the pivot number now, correct? Pivot number is coming on the second row. Now pivot number, top side number and downside number both should be zeros. So here this number and this number we need to change into zeros. That means first row we need to change and third row we need to change here. So first row changing means R1 plus is default. Now opposite of the number minus 4, that is plus 4, multiply pivot number coming on second row. 4R2 plus R1 gives new R1. Now same way third row we need to change. So opposite of minus 1, that is 1, multiply the pivot number coming row is second row plus R3 gives new R3. So equivalently we will get matrix. The first row, after using the calculator, we will get like 1, 0, minus 3 and minus 3. Second row, there is no change, 0, 1, minus 2 and minus 1. Third row, when we are using transformation, okay, the complete number it is changing into 0 here. So the matrix is in the canonical form now, because the first number 1, down number 0. The diagonal number it is 1 here, okay, second row first non-zero number is 1, top number 0, down number also 0, the third row fully zeros, correct? So the matrix is in the canonical form or row reduced echelon form now. Now we need to write the rank, okay, the rank of the matrix A and rank of the matrix AB. So I can write here rank of the matrix AB, okay, we need to calculate from there. And rank of the matrix A we need to write here, rank of A, and number of variables, that is n, how much, okay. So here rank of AB matrix means the full matrix. What is the rank? This is the non-zero row, this is the non-zero row, but the last one is completely zero row. So rank of AB is 2, correct? So rank of AB equal to 2. Now rank of A means only we need to take the A part, this A matrix part. How many non-zero rows are there? This is non-zero row, this is also non-zero row, but third one is 0 row. So there also rank equal to 2 here. I can write rank of A equal to 2. Now how many number of variables or number of unknowns? In our equation you can see we have X variable, we have Y variable, we have Z variable. So we have 3 variables are there, 3 unknowns are there. So we can write number of variables n equal to 3 or number of unknowns equal to 3. Now we will check one by one. For example, rank of A, B and rank of A both are same here, correct? Rank of AB is 2, rank of A also 2. So what is the meaning that one? That system is consistent. Consistent means we have solution, correct? We have solution. That is the meaning consistent. Now what is the number of variables here? Number of variables equal to 3 here. So rank is the small number, number of variables is big number, correct? So rank is 2, number of variables is 3. So rank of A less than number of unknowns, number of variables. So what is the meaning of that one? That means that system having infinite number of solutions. Okay, infinite number of solutions. Okay, so how we are taking that one? Rank of A less than number of variables. Now what is it? How many number of variables here? Number of variables is 3. Okay, minus what is the rank of the matrix? That is 2. 3 minus 2. 3 minus 2 means what? That is 1. Okay, the number of variables minus rank of the matrix A. Okay, it is equal to 1. So that means one variable we are taking as the free variable. Okay, one free variable will be there. One free variable will be there. So we will see what is that free variable. So what we are doing now? Now we are converting the last matrix into equation. See, the first number stand for x number, second number y, third number z, and the right side number, last one. Okay, so for example, first one, 1 multiply x, that is x, plus 0 multiply y, that is 0, plus minus 3 multiply z, that is minus 3z, equal to minus 3. So we can write the equation here. Okay, that is x minus 3z equal to minus 3. Now same way the second equation. What is second equation? 0 times x, 0. 1 times y, that is y. Minus 2 times z, that is minus 2z, equal to minus 1. Correct? So I can write, okay, I can write y minus, sorry, plus y minus 2z. Okay, y minus 2z equal to minus 1. Now the third row is completely 0, 0, 0, 0, correct? So there is nothing there. So one variable from out of this we are taken free variable, correct? So what is the free variable here we can take? Okay, from the first equation, for example, x equal to, we can write x equal to minus 3 plus 3z, because this minus 3z I am taken to next side. So minus 3 plus 3z. From the second equation we can take y equal to minus 2z, take to next side. So minus 1 plus 2z, correct? That means both x and y, if you need to calculate, you need to know y number, then only we can calculate x number and y number. So z variable we are taking as a free variable. So z means I am taking equal to z equal to z, that means a constant we are taking, z number we need to take. So for example, I am taking z equal to a constant, that is a free variable. Free variable means we can choose any value for that one. Okay, any value for that one we can choose. So for example, first equation, how it will change? X equal to minus 3 plus 3 times, instead of z we can write it as k or k1, whatever you are choosing. For example, I am choosing k1 because sometimes two free variables will be there, so k1 is better. So 3 times k1. From the second equation, y equal to minus 1 plus 2 times z, means 2 times k1. And the third one already we are taken z equal to a free variable, z equal to k1. Okay, I hope you are clear how we are writing. So this is we are calling the general solution of the system of linear equation. Okay, general solution of system of linear equation. Now otherwise we can write in matrix form like this. Okay, x y z, matrix form solution, general solution in matrix form, x y z equal to, first write the constant term plus k1 terms we are writing like a separate two matrices like this. For example, constant term in the first one, what is the constant term? Minus 3. So I am writing here minus 3. Second equation, what is the constant term? Minus 1. I can write minus 1. Third equation, there is no constant term here, so we can write it as 0. Now the k1 terms we are writing separately in the second matrix. See here 3k1. So k1 behind number is 3. Okay, and here 2k2. 2 multiply k1. So 2 is the behind number. In the third equation, k1. K1 behind number is 1 here. Okay, you can write 1. So this is calling the general solution of the system of linear equation. I hope you are clear how to calculate the general solution and how to write in matrix form that one. Now this matrix values -3, -1, 0. This is calling a particular solution or one of the solution for the system of equation, particular solution of the system of linear equation. So this is the way to calculate the system of equation solution. I hope you are clear this one. Okay, now when we are doing this type of question, okay, rank of A, B and rank of A, okay, rank of A, B and rank of A for non-homogeneous system, for example, okay, this one, these two are equal means we have a solution consistent. For example, if it is rank of A, B greater than rank of A, okay, then there is no solution. As I told you, there is no solution to this case because this number is bigger number 3. For example, this is 2. There is no solution in that case. Okay, so I hope you clear that one, how to do the general solution. Now I am going to the another question from here, this section. Find the inverse, how to calculate the inverse by using row transformation. Okay, inverse of a matrix by using row transformation. So calculating inverse matrix by using row transformation, how to do. So for example, here find the inverse of the matrix, A inverse of the matrix by using elementary row transformation. ERT means by using elementary row transformation. So we will go here. Here A matrix is there, 2, -1, 0, 0, 1, 1 and 1, 0, 1 here. So we need to start with the augmented matrix A and I matrix initially. A matrix and I matrix writing together. For example, what is the A matrix here? The given matrix 2, -1, 0, 0, 1, 1 and 1, 0, 1. Now write the I matrix. I matrix means the identity matrix, correct? So 1, 0, 0, 0, 1, 0 and 0, 0, 1. Okay, starting with this matrix, A matrix and I matrix. Now we are using the row transformation and changing the matrix into the row reduced echelon form or canonical form. So we will start that one. As I told you, first number should be 1. This is the first point we need to do. First number should be 1, but here it is not 1, it is 2. So we can check the down numbers. Here it is 0, here it is 1. So if we are interchanging third row and first row, we can do that one. Okay, so we need to change the first row and third row. If this is not possible, you can divide with the same number. So equivalently, the matrix we can write the third row we are writing as first. So 1, 0, 1 and 0, 0, 1. Full row we need to write, we need to change even I part also. Now the second row there is no change, 0, 1, 1, 0, 1 and 0. First row now become last row. So 2, -1, 0, 1, 0 and 0. I hope you are clear. Now what is the next operation we need to do? The first number, this is 1 here now, this is the pivot number coming on the first row. Now pivot number down number should be 0, but here it is 2. So we need to change this number into 0, correct? So which row we need to change? We need to change the third row. So as I told you, R3 plus is default. Now opposite of 2 number, that is -2. Multiply pivot number coming row is the first row. So -2 R1 plus R3 gives new R3. So how the matrix is changing we can do equivalently the matrix. Okay. So after changing we will get like first row there is no change, 1, 0, 1. You can check by calculator, 0, 0, 1. Second row also no change, 0, 1, 1, 0, 1, 0. But third row we are using this row transformation, -2 times R1 plus R3 gives new R3. So we are getting like 0, -1, -2, 1, 0 and minus 2. Now, so the first number is 1 now, the down numbers are 0 here. Now, second row starting number should be 1. So, here it is already 1. So, there is no problem. So, this is the pivot number now. Pivot number coming on the second row now. Now, pivot number, down number and top number should be zeros here. Here already 0. So, here we need to change this number into 0 here. So, which row we need to change? That is third row. So, R3 plus is default. Opposite of minus 1, that is plus 1, multiply pivot number coming row is the second row. Okay. So, equivalently the matrix, we need to change the matrix by using that row transformation. First row there is no change, 1, 0, 1, 0, 0, 1. Second row there is no change, 0, 1, 1, 0, 1, 0. But third row we need to change by using that transformation. Immediately we will get 0, 0, minus 1, 1, 1 and minus 2. Okay. You can check by calculator, that is same or not. So, first number is 1, next row non-zero, first starting non-zero number is 1, down number 0, up number 0. Now, we need to change this number. This number should be 1 here. So, which row again we are doing? Third row divided by the same number gives the new third row. Okay. So, equivalently the matrix, first row 1, 0, 1, 0, 0, 1. Second row 0, 1, 1, 0, 1, 0. Third row we are using that transformation, complete number we divide by minus 1. So, we will get 0, 0, minus 1 by minus 1 is 1, 1 by minus 1 is minus 1, 1 by minus 1 minus 1, minus 2 by minus 1 is 2. All the number divide by minus 1. So, we got here number 1 now. So, this is the pivot number now. Pivot number is coming on the third row. Now, what we do? Pivot number, top numbers should be zeros here. So, which rows we need to change? We need to change the first row and we need to change the second row. So, R1 plus is default here. Opposite of the number 1, that is minus 1. Multiply pivot number coming on third row. Same way here also, opposite of 1, minus 1, multiply pivot number coming on third row plus R2 is default, gives new R2. So, you can check by calculator these two transformation, how the matrix are changing. Equivalently, matrix, first row there is no change, we are changing. So, we are getting the answer 1, 0, 0, 1, 1 and minus 1. Second row also we need to change. We are getting 0, 1, 0, 1, 2 and minus 2. Third row there is no change. 0, 0, 1, minus 1, minus 1 and 2. I hope you are clear up to here. Okay. Now, the first matrix, the first part, it is in the canonical form now. Correct? It is in the row reduced echelon form. So, canonical form now. So, how we are writing this one? It is equal to, canonical form means it is the identity matrix. We can say like that, that is more clear. The first matrix now it is in identity matrix. Okay. So, it is of the form first matrix we are changed into identity matrix. That case, second matrix we are calling A inverse matrix. Second part, that means this part. Okay. So, write the answer here. What is A inverse? A inverse equal to matrix 1, 1, minus 1, 1, 2 and minus 2, minus 1, minus 1 and 2. So, this is the inverse of the matrix A. So, I hope you are clear. So, this section we are discussed how to find the rank of a matrix, and then we are discussed how to find the general solution of a system of linear equations, and third we are studied how to find the inverse of a matrix 2 by 2 or 3 by 3, whatever the order, we can calculate the inverse. Okay, now let me go to the 1.4 section. You can see vector spaces. 1.4 is vector spaces. So vector space means we have a non-empty set vectors x, y, z, and is said to be a vector space over the field of scalars alpha, beta, gamma, etc. Scalars under the operation vector addition and scalar multiplication, and it satisfies these 9 properties. Okay, so one is the V closed under vector addition, that is x plus y, x and y, for all x and y belongs to V, x plus y also belongs to V. If you are adding 2 vectors, that also should be a member of the vector space. And associative property, x plus y plus z equal to x plus y plus z. Addition is commutative, that means for all x plus y equal to y plus x. For all x and y belongs to V, x plus y equal to y plus x. Existence of identity property, there should have a 0 vector, calling 0 vector, 0 belongs to V, such that x plus 0 vector, if you are adding this vector with any other vector, you will get the same vector, x plus 0 equal to z, x equal to 0 plus x. Now existence of inverse element, for all x belongs to the vector space, for all the vectors there exists an x dash belongs to V, such that x plus x dash will be 0 vector equal to x dash plus x. So these are these 5 property under addition, vector addition. Now another property for scalar multiplications are there. V is closed under scalar multiplication, that is for all x belongs to V and alpha belongs to F, alpha x belongs to V, alpha multiply x, then vector and scalar multiplied, it should be a vector member of the vector space V. Okay, for all alpha belongs to the F set scalars. Now scalar multiplication is associative. Scalar multiplication is associative. That means alpha multiply beta x equal to alpha beta multiply x. And existence of unity element. There will be, if one is the unity a member in the F, this is important, one belongs to the F field of scalars, and one multiply any vector should be same as the x vector for all x belongs to V. And also we have distributive laws, alpha plus beta multiply x equal to alpha x plus beta x, and alpha multiply x plus y equal to alpha x plus alpha y. So this should satisfy. So all 9 property is satisfying means it is a vector space over the field f of scalars, especially when we are checking the vector space. Okay, first these properties keep in your mind. First property, vector addition, closed or not. Okay, and existence of identity, there is a 0 element or not. Existence of inverse element exists or not. And V is closed under scalar multiplication or not. And existence of unity property, unity element multiply the vector equal to the same vector or not. These 5 property always very careful. So logically check the set, is it satisfies these 5 properties or not. So immediately you can identify that is vector space or not. After that you can check the other properties, associative property, commutative, identity. Okay, commutative and scalar multiplication is associative, distributive laws. Okay, these we can check the later also. Okay, so these properties important logical properties. So all these 9 properties for vector space, if all satisfied, it is a vector space. One of the property violating means it is not a vector space over the field f of scalars. So I am not telling detail, just seeing the discussing the ideas. Now vector subspace or subspace, what is the meaning of subspace or vector subspace? Subspace means, okay, for example, W is a subset of non-empty subset of V. W is a non-empty subset of V. Okay, then if it is a vector space, W itself is a vector space over the field under the same operations in V. Okay, under the same operations in V, that means vector addition and scalar multiplication, whatever we defined in V, under the same operation, if W itself is a vector space, means W itself satisfy all the 9 conditions of the vector space, means we are calling W is a subspace of V. But as per this theorem, you remember theorem W is a non-empty subset of a vector space V over a field F, then W is a subspace of F if and only if the following conditions are satisfied. So W subspace or not, we can, as per this theorem, we can check only these 2 conditions. What are the 2 conditions? For all x, y belongs to W, take any 2 vectors from the subset W. Calculate the x plus y, closure property in addition. Is it always a member? Is it a member of W or not? It should be a member of the W. And for all vectors in W and one scalar belongs to F, all scalars belongs to F, alpha x also belongs to W. Okay, two vectors belongs to W, closure property satisfied, it should satisfy x plus y belongs to W, and closure property in multiply, okay, closed under scalar multiplication also, alpha x plus belongs to W also should satisfy. Or we can check this one condition together, okay, for subspace or not. So these are the two conditions for the checking subspace or not. So vector space we have 9 properties we need to check, but subspace, okay, if it satisfies these two conditions, it will be a subspace of that vector space. Okay, we will do one or two simple examples here from vector space and subspace. For example, here one question. Let V equal to R cube. Okay, set of all 3 tuples. Vector space is R cube. Okay, the set V is R cube over the field F of the real number. Real number means any number. 1, 2, 3, minus 1, minus 3. Okay, minus 1.1, 1.1, any numbers. Vectors are from R cube. Now what we are telling, if you are taking any two vectors from R cube, x1, x2, x3, y1, y2, y3, the vector addition x plus y equal to x1 plus y1, the first number x numbers add, comma y numbers add, x2 plus y2, comma z numbers add, x3 plus y3. Okay, and scalar multiplication, how we are defining, alpha multiply x equal to alpha x1 comma alpha x2 comma 0. So what we need to do when we are multiplying a scalar with x, how the scalar multiplication defining here, alpha multiply the x number x1, alpha with x1, alpha multiply with x2 number, but third number we are writing 0. So this is the vector addition and scalar multiplication defined here. So what is the question? Show that V is not a vector space over the field F of the scalars. Okay, show that V is not a vector space over the field of scalars. Now, not a vector space, as I told you, not a vector space checking time. First check these 5 properties. First one, fourth one, fifth one, sixth one, eighth one. Any one of these property violating or not. If any property violating, immediately you can write. And when you are thinking also first 5 property in vector addition, okay, another one is the multiplication, scalar multiplication related properties. Okay, so when we are going to here, you see, okay, the operations here, whatever the operation defined here, x plus y means x1 plus y1, x2 plus y2 plus x3 plus y3. This is usual addition of two vectors, correct? Usual addition of two vectors, because x1 plus x numbers add, comma y numbers add, comma z numbers add. But when we are coming to the scalar multiplication, there is some unusual things are there, correct? There is some unusual things are there. What are the unusual things actually? Alpha x1, alpha x2, but third number is 0 here, correct? Third number is 0 here. Alpha x1, alpha x2 and 0. So this multiplication related properties, so this case we need to think about the multiplication related properties. What are the multiplication related properties actually? V is closed under scalar multiplication or not? Scalar multiplication associative, existence of unity, distributive law, especially the closed under scalar multiplication, closed under scalar multiplication and existence of unity elements. For example, here I am taking 2 vectors here. For example, x equal to, for example, any 2 vectors. I am taking like 1, minus 2 and 3, one vector. Okay. And second vector y equal to, for example, I can take like, okay, 2, 5 and minus 4. Okay. These are the 2 vectors belongs to V. V means R cube or cube. Okay. Now take a scalar number alpha equal to, for example, I am taking minus 2. Okay. Alpha equal to any number you can take because it is a set of real numbers field. F equal to R. Now when we are doing alpha x, for example, here alpha multiply x. Alpha means, for example, I am taking minus 2 multiply x means 1, minus 2 and 3. Correct. So what will be the answer? scalar multiplication is defined here. Alpha x1, alpha x2, 0. So here x1 is 1, x2 is minus 2, x3 is 3. Correct? So alpha minus 2 multiply x1 minus 2. Minus 2 multiply minus 2, that is 4. Then third number should be 0 as per our scalar multiplication. Correct? Minus 2, 4 and 0. This is also belongs to the vector. Correct? Vector, because what is the vector space actually? R cube. R cube means any 3 tuple numbers, we can take that one, minus 3 and 4 and 0. This is a number vector belongs to R cube. So this is no problem. But when we are calculating the unity property, 1 multiply x equal to x, this property, can we check this one? So 1 multiply, what is the x here? 1 minus 2, 3. Correct? So equal to, as per the scalar multiplication, how we are defining? 1 multiply 1, that is 1. 1 multiply minus 2, that is minus 2. But third number should be 0 as per our multiply. So 0. Is it same as x? No, it is not same as x. Correct? Because x means what? 1, minus 2 and 3. But here the third number is 0 here. Correct? So it is not same as x. So it is violating the unity property. Correct? So this property it is violating. So what we can say? V is not a vector space. V is not a vector space over F under the vector addition and scalar multiplication defined in our question. I hope you are clear this question. Okay. Now, when we are going to this question, V equal to R cube. Okay. V equal to R cube. The set of all 3 tuples of real numbers with the second component is 1. Second component should be 1. So how we actually V equal to the set of all 3 tuples. 3 numbers should be there. Correct? So first number, second number should be 1. So comma 1, third number any C. First number and third number any number. A and C belongs to F means any real numbers. But second number should be 1 here. Now what is the question actually? Define the vector addition and scalar multiplication as follows. X plus y equal to x1 plus y1, x2 plus y2, x3 plus y3. This is usual vector addition. Okay. And alpha x equal to alpha x1, alpha x2, alpha x3. This is also usual scalar multiplication. Correct? In R power n. Because alpha x1, alpha x2, alpha x3. Previous question it was 0. That is why it was not usual. So here it is usual. So we need to check V is not a vector space over F. Not a vector space. Okay. That means we need to check all 9 property. One of the property it is violating. So I told you what are the important properties in the vector space. That 5 properties we can check first. If it is satisfied, we can go all the 9 properties. Okay. So for example, I am taking 2 vectors here. X equal to. Okay. What is the condition? Middle number should be 1. For example, x equal to. Okay. Instead of a, any number you can take minus 2. Second component should be 1. Third component I am taking 3. Now y equal to another vector I am taking. First number is 3. Second number should be 1. Third number I can take any number, that means minus 4. Now first property I am checking x plus y, the closure property under vector addition. So x plus y equal to, okay, x plus y equal to, what is x actually? Minus 2, 1 and 3, plus what is y? 3, 1 and minus 4. Okay, so we can add these two. So how we are getting? First numbers add, because vector addition is defined here. X numbers add, comma y numbers add, comma z numbers add. So minus 2 plus 3, that is 1. 1 plus 1, that is 2. 3 plus minus 4, that is minus 1. Correct? Is it a member of the vector space? No. Why it is no? It is doesn't belongs to V, because the second component should be 1. Okay, our vector space is second vector is not vector space. Our set is the second component should be 1, but here second component is not 1. So it is not a vector space. So we can write V is not a vector space. Correct? V is not a vector space over F. V is not a vector space over F. Now this is one of the property it is violating, closure property. Now also you can think about immediately. See, as I told you, zero existence of identity, correct? This property, existence of additive identity. Zero element should be there in the vector space. Is there any zero element in this vector space? What we discussed now, there is no zero element, because zero element means 0, 0, 0, correct? This element also doesn't belongs to V. Immediately you can identify when we are thinking, because here middle number should be 1. As per our question, all the vector middle number should be 1. So 0, 0, 0, this vector, it will not be in the vector space. So 0 existence of identity, additive identity, that property also easily it is violating. So this property also easily we can check it. Okay, I hope you clear. So this is not a vector space over the field of scalars. Now we will go to the another example for subspace. For example, here question number A, let V equal to R cube. Vector space is R cube. V equal to R cube. Determine which of the following subsets of V are subspace of V. Okay, we need to check subspace or not. That is the question here. Which of the following are subspace of V? So for example, here when we are taking how the W subset, W equal to 0, 0, C. First number should be 0. Second number should be 0. Third number, any number you can take. Okay, in the field. Field means real numbers. Okay, so we will check it. This is a subspace or not. For example, when we are taking, okay, X equal to, first number should be 0. Second number should be 0. Third number, any number. For example, I am taking 5. And Y equal to, for example, I am taking first number 0, second number 0, and minus 9, for example, here. Okay, now when we are doing X plus Y, what are the two properties of the subspace? X plus Y we need to check, alpha X we need to check, correct? So for example, X plus Y, 0, 0, 5 plus 0, 0, minus 9. Okay, so you can think what is the answer getting? 0, 0, 5 plus minus 9 means usual vector addition and scalar multiplication. 5 plus minus 9 means minus 4. Is it a member of the W again? Yes, it is a member of W, because first number 0, second number 0, third number any number. So when we are taking two vectors from W, any two vectors, when we are adding, again that is a vector from W. So first property is satisfying. You can think about any number, it is not satisfying this case or not. Any we can take, for example 0, 0, A and plus 0, 0, B. Any number if you are taking, when we are adding 0, 0, we are getting A plus B. A plus B also a real number. So it should be a member of W always. There is nothing to confuse that one. So first property satisfying. Now second one we can check it. Alpha multiply X. Now for example, alpha I am taking minus 5. So when we are checking here, minus 5 multiply X, 0, 0, 5. So how we are multiplying? Each number we multiply with outside. Usual scalar multiplication. So minus 5 multiply 0, 0. Minus 5 multiply 0, 0. Minus 5 multiply minus 5, minus 25. Correct? Is it a member of W? Yes, it is a member of W, because first number is 0, second number also 0. Third number, any number we can take. So it is a member of the W. So second property also satisfying. Second property generally also you can think alpha multiply any vector you are taking 0, 0, C like this. When we are multiplying alpha multiply 0, that is 0, correct? So first number will be 0. Alpha multiply 0, again it will be 0. Alpha multiply C, alpha C, it will be a number. So it should be a number of W. So there is no confusion here also. So first property satisfying, second property satisfying. So W is a subspace. W is a subspace of V. And clearly you can assume, is it a 0 member? 0, 0, 0 belongs to W? Yes. 0, 0, 0 also belongs to W. Why? Because first number already it is 0. Second number is already 0. Third number you can take any number. Correct? 0, 0, C. First number 0, second number 0. Third you can take any number. In case 0 also you can take. For example, if you are taking 0, 0, 0, 0, you will get a 0 member, correct? 0, 0, 0 also belongs to the set W. 0 members also there. So automatically you can think that is W is a subspace. Okay. So when you are checking subspace also, you can think about logically, is it come 0, 0, 0 in that set or no? If it is not, immediately you can write logically it is not a subspace of V here. So I hope you clear. Now when we are coming to the B part, okay, W equal to set of all triple ABC, ordered triple ABC, A greater than or equal to 0. A greater than or equal to 0. What is the condition here? The first number, A greater than or equal to 0. First number should be a positive number or 0. Okay. So we will check this one. For example, I am taking x equal to one vector. First number should be greater than or equal to 0. For example, I am taking 2. Okay, and the second number, any number, I am taking 5. Third number, any number, I am taking -3. Okay, now y equal to, I am taking the numbers, first number should be positive 3, second numbers, any number, -2, third number, any number, for example 5, like this. Okay, and alpha I am taking like -5. Okay, now immediately you can think subspace or not, that is the question. So x plus y equal to, okay, now when we are thinking this one, x plus y, okay, 2 plus 3, usual vector addition, that is 5, 5 plus -2, that is 3, -3 plus 5, that is 2, correct? Is it a member of W? Because we are taken one vector from W, another vector from W, and alpha belongs to -5. Again, x plus 5, is it a member? Yes, because the first number is positive here, 5. It is greater than or equal to 0, correct? So this is a member of W. Second and third, any number, no issue. So generally you can think, for example, you have A1, B1, C1 plus A2, B2, C2, correct? So here A1 should be greater than or equal to 0. Here A2 should be greater than or equal to 0. So A1 plus A2 also greater than or equal to 0, correct? So first number always it will come greater than or equal to 0. So there is no problem. So, so the closure property under addition, it is satisfying. Whenever you are doing closure property under addition, it is satisfying. Now when we are coming to the scalar multiplication property, okay, scalar multiplication property, alpha multiply x. What is alpha? We are taken -5. Multiply what is x? 2, 5, -3, correct? When we are multiplying this one, what answer getting? -5 multiply 2, -10. Usual scalar multiplication. -5 multiply 5, -25. -5 multiply -3, that is 15, correct? So what happened actually? Here the first number is not greater than or equal to 0. Not greater than or equal to 0. Not a positive number or 0. It is a negative number. So this one doesn't belongs to W. That means W is not a subspace. Okay. W is not a subspace of V. Okay. I hope you are clear. Okay. But see this one, second, alpha multiply x, when you are checking generally, alpha multiply x. See, if you are taking alpha number positive, for example 2, then if you multiply with this x, that is 2, 5, -3, you will get positive 2, 5, -3. We need to check all the possibilities. See here when we are doing 2 multiply 2, 4, 2 multiply 5, 10, 2 multiply -3, -6. It is belongs to W, but not always. It is not always the alpha, not always alpha, correct? If alpha is negative number, if you are choosing, this will not come. So generally we need to think always alpha multiply x number positive, that is A, B, C. For example, when we are doing alpha multiply A number is greater than or equal to 0. But when we are doing alpha number negative number multiply a positive number means it will be a negative. So it will be less than 0, correct? So like that we need to think which number we need to choose. Okay, so that that property violate, we can show that one. So I hope you are clear. This is not a subspace of the vector space here. Okay, also you can think, is it 0, 0 element, 0 belongs to W? It is belongs to, because first element you can take 0. second also 0, third also 0, you can select, it is member. But the only problem, scalar multiplication is not closed here. So it is not a vector subspace of V. So I hope you are clear that section 1.4. Now I am coming to the 1.5 section. Okay, 1.5 section. 1.5 is linear independence. Okay, so this section we are studying linear combination, we are studying linearly dependent, linearly independent. What is the meaning we are studying here? Okay, so linear combination means one vector x is a linear combination of x1, x2 up to xn. Okay, how can we write that one? X equal to alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3 plus alpha n xn. If we can write like this, we can say x is a linear combination of x1, x2 up to xn. You can see one example here. Okay, I am not going detail. Linearly dependent and linearly independent. Linearly dependent means the linear combination alpha 1 x1 plus alpha 2 x2 plus alpha n xn equal to 0 means at least one of the alpha I not equal to 0. Okay, linearly dependent, alpha 1, alpha 2, alpha 3, alpha n, one of the alpha I number you are getting non-zero number 1, 2, 3 like that. But linearly independent means when we are taking linear combination equal to 0, all the alpha number you are getting 0, alpha 1, alpha 2, etc., alpha n equal to 0 here. So it is calling linearly independent vectors. Now when we are coming to the practical questions, practically, okay, so how we are checking linearly independent or not, or linearly dependent or not? For example, if you are getting a vectors to check linearly independent or not, just calculate rank of A and number of variables. Rank of A equal to number of variables means that vectors are linearly independent vectors. Rank of A equal to number of variables means linearly independent vectors. If rank of A less than number of unknown means that vectors are linearly dependent vectors. Okay, linearly dependent vectors. Now here I am giving one shortcut also. Okay, you can practice that also, but I am not much discussing that one. If linearly independent, determinant of A should be not equal to 0. If linearly dependent means determinant A you are getting 0. Okay, this also you can check by shortcut. Determinant A not equal to 0, linearly independent. Determinant A 0 if it is linearly dependent. Or we can use the rank method. Rank of A equal to number of variable, linearly independent. Rank of A less than n, linearly dependent. Now to check the linear combination exists or not. Linear combination exists or not. First you need to check this one. Rank of AB and rank of A should be same. Okay, then only linear combination exists. Rank of A equal to rank of AB. If rank of AB greater than rank of A means linear combination not exist, because there is no solution that system. Now if rank of A equal to number of variables means linear combination will be unique, and if rank of A less than number of variables means there are many linear combination, infinite number of solution will be there. So linear combination, more than one linear combination we can write. Okay, so this is the condition for linear combination and independent dependent. Okay, let me go to some examples here. For example, the first one, write the vectors. Okay, write the vectors 1, 7, minus 4 as a linear combination. We need to write linear combination of the vectors x1 and x2. X vector we need to write as a linear combination of the vectors x1 and x2. So we will start this question. You know, linear combination means here we have x vector, we need to write in terms of x1 and x2. So what is the linear combination actually? Vector x equal to alpha 1 x1 plus alpha 2 x2, like that we need to write. Okay, can we write like this or not? That is the question. That is the meaning linear combination exists or not. So what we need to do actually, if you want to write, we need to calculate alpha 1. We need to calculate what is alpha 2. x1 and x2 already given in the question. X also given. We need to calculate what is alpha 1 and what is alpha 2 here. So, let me go this one. Okay, so First apply x vector here. X vector means x vectors means 1 7 minus 4 equal to alpha 1. X1 means 1 minus 3 2 plus alpha 2 multiply x2 means 2 minus 1 and 1. Now simplify this one. So 1 7 minus 4 equal to, you can multiply alpha 1 to inside. So alpha 1 minus 3 alpha 1 2 alpha 1 plus alpha 2 multiply inside 2 alpha 2 minus 1 alpha 2 1 alpha 2. Then add these two. So alpha 1 plus 2 alpha 2, x numbers add, y numbers add, minus 3 alpha 1 minus alpha 2 comma 2 alpha 1 plus 1 alpha 2 equal to 1 7 minus 4. Now two vectors are equal means x numbers are equal, y numbers are equal, z numbers are equal. So we will get alpha 1 plus 2 alpha 2 equal to 1. X numbers take, first numbers are equal. Second number minus 3 alpha 1 minus alpha 2 equal to 7. Third number 2 alpha 1 plus alpha 2 equal to minus 4. From this we need to calculate what is alpha 1, what is alpha 2, what is alpha 3. Okay, if we are getting these numbers alpha 1, alpha 2, alpha 3, linear combination exists, so that we can write the linear combination. Okay, now when we are doing question, okay, you can start directly from here also, a b equal to, directly from here you can start. You can avoid these steps. First write this linear combination step. After that directly you can jump to here, a b matrix equal to matrix. Write a matrix and b matrix. A matrix means you can see the first vector 1 minus 3 2, you can write like column wise, 1 minus 3 2. Second one x2 vector, write the column wise, 2 minus 1 1. Then x vector, what is x vector? 1 7 minus 4. Okay, this is a b matrix, a and b matrix. Okay, now change this matrix into the canonical form using row transformation. Okay, so exam all you can avoid these steps. You can directly come to here a b matrix and you can reduce by row transformation. For example, here I am going to reduce the row transformation using first number we are calling pivot number, that should be 1. It is already 1 here. So down numbers minus 3 and minus 2, minus 3 and 2 we need to change into 0. So second row we need to change, third row we need to change. So R2 plus is default, R3 plus is default. Now opposite of minus 3 number plus 3, multiply pivot number coming on the first row. So 3 multiply R1. Now opposite of 2 minus 2, pivot number coming on first row, so minus 2 R1. Okay, so when we are applying these row transformations equivalently, you will get matrix. First row no change, 1 2 1. Second row use that row transformation, equivalently you will get 0 5 10. Third row becomes 0 minus 3 minus 6. You can check by calculator, 0 minus 3 minus 6. Now what we are doing the next is that, now the first number we changed, down number we changed 0. Now second row first non-zero number should be 1. So here it should be 1. So second row completely divide by 5, get new second row. So equivalently the matrix, first row there is no change, 1 2 1. Second row complete number divide by 5. So 0 by 5 0, 5 by 5 1, 10 by 5 2. Third row same, 0 minus 3 minus 6. Now again the pivot number is this one, it is coming on second row. So pivot number, top number and down number should be 0. So this number we need to change, this number we need to change. So first row we need to change row number 1. and third row we need to change. So R1 plus is default, opposite of 2, that is minus 2, multiply pivot number coming on second row, and here the R3 plus is default, opposite of minus 3, 3, multiply pivot number coming on second row. So equivalently we will get matrix. Okay, I am writing the numbers here directly. You can check by calculator. 1 0 minus 3, 0 1 2, and third row 0 0 0. I hope you are clear. 0 0 and 0. So this is the canonical form, row reduced echelon form or reduced canonical form. So you can check what is the rank of AB and what is rank of A and how many number of variables n equal to. Okay, so rank of AB means here it is 2. 2 non-zero rows are there fully. Rank of A also 2. Now how many number of variables you can check it here. Okay, only 2 variables, correct? It's not alpha 3, it was alpha 1 and alpha 2 only. Okay, only 2 variable. You can see here alpha 1 and alpha 2. By mistake I told before alpha 3. So here we can write 2 variables. So what we can conclude, rank of AB equal to rank of A means, what is the meaning? Consistent. We have solution. We have solution. That means we can find alpha 1 and we can find alpha 2. Now it is same as number of variables. What we discussed in that flowchart. If it is same as the number of variables means we can say the system having unique solution. Only one solution, only one linear combination. So consistent means linear combination exists. How many linear combination? Unique solution, unique linear combination. First row, I am taken alpha 1 and alpha 2 here. So alpha 1, alpha 2, because here unknown is alpha 1 and alpha 2. So here first row becomes row number 1, alpha 1 multiply 1, that is alpha 1 equal to minus 3. Second row becomes alpha 2 multiply 1. So alpha 2 equal to 2, because here 1 multiply alpha 1, alpha 1, 0 multiply alpha 2, 0, equal to minus 3. Here also second row 1 multiply alpha 2 equal to 2. So we got alpha 1 and alpha 2. So we can write the linear combination. What is the linear combination? Linear combination is, just apply here, x equal to alpha 1 x1 plus x equal to alpha 1, that is minus 3 x1 plus alpha 2, that is 2 x2, 2 multiply x2. This is the linear combination. So I hope you are clear this one, how to do, how to check linear combination exist or not. Okay, linear combination exist or not. Now let me come to the linear independence and dependence questions now. So next example we can go. Show that the vectors x1 equal to, x2 equal to and x3 equal to in R cube are linearly dependent. We need to check linearly dependent or not. We need to show that one. Okay, so linearly dependent or independent, we need to start from the linear combination alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3 equal to 0. Correct? Linear combination equal to 0. Now from here we need to calculate what is alpha 1, what is alpha 2, what is alpha 3. Correct? These three number. Okay, if these three number, okay, when we are calculating these three number alpha 1, alpha 2, if at least one alpha I not equal to 0, for example alpha 1 1, alpha 2 0, alpha 3 0, at least one of the alpha number should be not 0, then it is linearly dependent. Or all are 0 means it is calling linearly independent. So for that I already given one method how to check linearly independent or not. Just we need to calculate rank of A and number of variable. Rank of A equal to number of variable, linearly independent. Rank of A less than number of variable, linearly dependent. So here I am starting with the A matrix. Okay, only we start with the A matrix. Okay, so we will go this one. A matrix means, what is A matrix? X1 vectors write in column wise. 1, minus 2, 1. X2 vector 2, 1, minus 1. X3 vector 7, minus 4 and 1. Okay, or you can simplify this one. Alpha 1 multiply x1 is 1 minus 2 1 plus alpha 2 multiply x2 means 2 1 minus 1 plus alpha 3 multiply 7 minus 4 1 equal to 0. 0 means 0 0 0. After that, here you can add, you can simplify what is the first vector. Alpha 1 plus 2 alpha 2 plus 7 alpha 3 comma, write the second vector comma, write the third vector equal to 0 comma 0 comma 0. Then first vector equal to 0, second vector equal to 0, third vector equal to 0, so that you will get 3 equations. After that, you can come to the matrix for solution. So I am doing here the short way. Directly we can start with A matrix. A equal to this one. Now apply the row transformation and change into the row reduced echelon form or canonical form. I am using all the question row reduced echelon form. You can change row reduced form also, okay, or echelon form also, but here I am using all the question this method. Okay, so first number is 1. Here already it is 1. That number is the pivot number. It is coming on the first row. Now pivot number down number should be 0. So this number and this number we need to change into 0. So I am using the row transformation. Already you familiar with the row transformation. Second row we need to change. Third row we need to change. So R2 plus is default. R3 plus is default. Opposite of minus 2 plus 2 multiply pivot number coming first row. Opposite of 1 minus 1 multiply pivot number coming first row. So you can do this one by using calculator. So equivalently you will get a matrix. The matrix first row no change 1 2 7. Okay, the second row becomes 0 5 10 and the third row becomes 0 minus 3 and minus 6. Okay, now the second row we are going. Second row first number should be 1. So this number should be 1. So R2 divided by 5 gives new R2. Okay. So equivalently the matrix becomes 1 2 7 0 1 2 0 minus 3 minus 6. This question, it is previous section also we are taken same model, same questions. So it is easy to understand the ideas. Now the pivot number is coming on the second row. So pivot number down number and top number should be 0. So minus 2 multiply R2 plus R1 gives R1 and 3 multiply R2 plus R3 gives R3 we need to do. So equivalently we will get the matrix. Okay, we are getting the matrix like 1 0 and 3, 0 1 and 2, 0 0 and 0. So it is in canonical form now. So we are just writing what is rank of the matrix A and what is in how many number of variables here. So here rank equal to number of non-zero rows 2. How many variables are here? Alpha 1, alpha 2, alpha 3. That means it is 3. Rank equal to 2, number of variables is 3. So rank of A less than number of variables, correct? Rank of A less than number of variables means linearly dependent. That vectors are linearly dependent. Okay, I hope you are clear. This flowchart it is mentioned already. This flowchart, see, linearly dependent means rank of A less than n, or one of the method is determinant A should be 0. So I will explain this question by using that shortcut also. If you are checking this question, the second method, okay, I will go here or. Okay, what you calculate? Determinant of A, just calculate. That means determinant of A matrix already here 1 2 7. Okay, and minus 2 1 minus 4 1 2 7 minus 2 1 minus 4 1 minus 1 and 1. Okay, when you are calculating this determinant, we studied already in 1.2 section determinant. If you are getting determinant equal to 0, then it is linearly dependent vectors. Okay, so how to calculate determinant? Take one of the row, for example first row here. Okay, so the first row, first number 1, second number 2, third number 7. Alternative give first plus sign, second minus sign, third plus sign. Now when we are calculating determinant, for example first number is 1. 1 coming, row and column delete. Remaining numbers determinant. That means determinant 1 minus 4, 1 minus 1, 1. Okay, determinant 1 minus 4 minus 1, 1. Okay, now second number is 2. Take 2 number coming, row and column delete. Remaining number here minus 2, minus 4, 1 and 1. Okay, so I am writing here determinant minus 2, minus 4, 1 and 1. Plus 7, third number. 7 coming, row and column delete. Remaining determinant minus 2, 1, 1, minus 1. Now calculate the determinant value. So equal to, okay, equal to 1 multiply cross multiply here, 1 multiply 1 minus of numbers multiply, minus 1 multiply minus 4. Now here minus 2 multiply, here also cross, minus 2 multiply 1 minus 1 multiply minus 4. Now plus 7 multiply, minus 2 multiply minus 1 minus 1 multiply 1. You can calculate this determinant value, how much you are getting. Use the calculator. So you will get 0 because 1 multiply 1, that is 1 minus 4. Okay, so 1 minus 4, then minus 2 multiply minus 2 plus 4. So we can write minus 2 multiply plus 2, correct? Then last one plus 7 multiply 2 and minus 1. So plus 7. Automatically you will get answer equal to 0. So if determinant A equal to 0, meaning linearly dependent. Okay, if not equal to 0, linearly independent. So this method also you can use. This is one short idea. Okay, instead of row transformations you doing, also you can do, both are same lengthy, not much difference. Okay, this also you can utilize that one. Okay, now one more question from linearly independent or dependent. Show that the vectors x1 equal to, x2 equal to and x3 equal to in R cube are linearly independent. Okay, are linearly independent. So we will start. Take the linear combination alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3 equal to 0. Now start from A matrix. From here we need to calculate what is alpha 1, alpha 2, alpha 3, these three number. If all 0, linearly independent. Or we are checking rank of A equal to number of variable or not. Rank of A equal to number of variable, linearly independent. Or determinant A not equal to 0. So for example here A equal to the matrix first vector in column wise 1 2 minus 3, second vector 1 minus 3 2, 2 -1 and 5. So change the matrix into row reduced echelon form or canonical form by using row transformation. So here first number is 1, this is the pivot number. Now pivot down number should be zeros. So second row we need to change, third row we need to change here. So R2 plus is default, R3 plus is default. Opposite of 2 -2 multiply pivot number coming on first row. Opposite of -3 3 pivot number coming on first row. So equivalently matrix. Okay, you can check the number. First row there is no change, 1 1 2. Second row you will get, when we are using calculator, 0 -5 -5. Third row you are getting 0 5 11. Now this number is pivot. Now second row non-zero number starting should be 1. So second row we are divided by -5 gives new second row. So equivalently the matrix becomes first row 1 1 and 2. Second row complete number divided by -5 0 1 1. Third row becomes 0 5 11. There is no change. Now so now this is the pivot number, it is coming on second row. So pivot number, top number and down number should be 0. So we need to change the first row and we need to change the third row again. So R1 plus default, R3 plus default. Opposite of 1 -1 multiply pivot number coming on second row. Opposite of 5 -5 multiply pivot number coming on second row. So equivalently the matrix becomes first row when we are using calculator, okay, you will get 1 0 0. Second row becomes 0 1 0 1 and 1. Second row 0 1 and 1. Now third row. Okay, third row when we are changing, you will get 0 0 6 0 0 6. Now when we are going to the next operation, this number, third row non-zero number starting should be 1. So we need to divide third row divided by 6 gives new third row. So equivalently the matrix becomes, you can check all numbers by calculator, if there is any mistake just correct it. So 1 0 0 0 1 and 1, and here 0 0 and 1, correct. Now what we need to do, this is the pivot number, pivot is on third row. Now pivot number, top number should be zeros. We can change that row. So we can do the second row, we are changing, R2 plus is default, opposite of 1 -1 multiply R3. So equivalently we will get matrix 1 0 0 0 1 0 and 0 0 1 0 0 1 here. Okay, now let me go again. So we are getting the row reduced echelon form. So write what is rank of A matrix. What are the, how many number of variables we can write. Here rank of A equal to 3. There are 3 non-zero rows. Number of variables also 3 because alpha 1, alpha 2, alpha 3. So both are same. Rank of A equal to number of variables. So what we can say, rank of A equal to number of variables means the system is linearly independent. The system is linearly independent. Okay, so I hope you are clear. So our vectors, 3 vectors are linearly independent. Now the same question we can do by using determinant like this. Just to calculate what is determinant of the matrix A. That is determinant of 1 1 2 2 minus 3, minus 1, minus 3, 2, 5. Okay, the row reduced canonical form, that method is the standard method. You can follow, that is more better, because you can do any question that one. This is only by this one determinant method only for square matrices. So we can go that one. So 1, 1, 2, 2 minus 3 minus 1, minus 3, 2 and 5. Now expand by using first row, first number plus sign first, then alternative minus and plus. Now we are writing first number 1, second number also 1, third number 2. Now the first number 1 coming row and column we delete. Take the remaining numbers. Remaining numbers are minus 3, minus 1, 2 and 5. So I am writing here minus 3, minus 1, 2, 5. Now the second one. Second number 1. Coming row and column delete. What are the remaining? 2, minus 1, minus 3, 5. So we can write determinant 2, minus 1, minus 3 and 5. Now plus 2. 2 coming row delete, column delete. So determinant 2, minus 3, minus 3 and 2. Now we are calculating equal to 1 multiply, plus 1 means 1. Multiply, cross multiply here, minus 3 multiply 5, minus 2 multiply minus 1, minus 1 multiply, cross multiply 2 multiply 5 minus 3 multiply minus 1, plus 2 multiply 2 minus 3 multiply minus 3. Now we can set by calculator. 1 multiply minus 3 multiply 5 means minus 15. Minus of minus 2 plus 2. Correct? Minus 15 plus 2. Now minus 1 multiply 2 multiply 5 10 minus 3 multiply 1 minus 3, correct? So minus 1 multiply 10 minus 3. Okay. Now plus 2 multiply 2 4 minus 3 multiply 3, that is 9. So 2 multiply 4 minus 9. So totally you are getting equal to minus 30. You can check it the number. So this is not equal to 0, correct? Not equal to 0. That means it is linearly independent. So I hope you are clear. This determinant method and row transformation method, both are almost same steps only. Okay, you can follow both. Okay, so I hope you are clear. 1.5 section, how to check linearly independent or not, how to calculate the linear combination of vectors. Now we will go to the 1.6 section. It is just a continuation of 1.5, basis and rank. Okay, what is the meaning basis and what is the meaning of rank of a matrix, and we can say what is the meaning dimension of the vector space. So basis means a set of vectors b equal to x1 x2 up to xn is a basis. It should be linearly independent first. Already we studied last section how to check linearly independent or not. And every vector in vector space can be expressed as the linear combination of x1, x2 and xn. That means B span V or B generate V. The set B will generate all the vectors in the vector space. Okay, that means in the vector space all the vector we can write as a linear combination of x1, x2 up to xn. Now dimension, how many elements in the basis of a vector space is called the dimension of the vector space, and it is denoted by dim V, dimension of V, dimension of the vector space. So number of elements of the basis we are calling dimension of the vector space. We can write by dim V. Now there are some standard bases. For example, R square standard basis is E1 1 0, E2 equal to 0 1. Okay, standard unit vectors in the R square. Dimension of R square equal to 2 because there are two vectors here. So dimension is R square. Number of elements of the basis of the vector space is calling dimension. So here in the basis there are E1 and E2, two vectors. So dimension of R square equal to 2. Now when we are going R cube, okay, basis is E1, E2, E3. E1 means 1 0 0, E2 means 0 1 0, E3 means 0 0 1. Dimension of R cube means 3 because there are three vectors in the basis. Now generally dimension of Rn means n. R2 2, R3 3. So dimension of Rn means it is n. Now the second space Pnx. Pnx means vector space of all polynomials of degree less than or equal to n. Vector space of all polynomials degree less than or equal to n. For example, P1x. P1x means the first degree maximum polynomial. Polynomial of degree 1. That means x power 1 maximum. So polynomial of degree 1 P1x. What is the basis? 1 comma x. Using 1 comma x you can generate any first degree polynomial. What is the dimension of P1x? 2 because 1 and x. Dimension of P1x equal to 2. P1 means 2. Now when we are going P2x, second degree polynomials maximum. Second degree or less. For example, x plus x square, 5 plus x square. Like that maximum degree 2. 5 plus x. This is x degree 1 only. So maximum 2. That is the meaning P2x. Set of all polynomials degree less than or equal to n. Less than or equal to 2. Less than or equal to 1 like that. So what is the what are the basis elements of P2x? 1 comma x square. Using these three vectors you can generate any second degree polynomial. That is the meaning. Okay, so dimension of P2x equal to 3. So generally dimension of Pnx equal to n plus 1 because P2 means 3, P1 means 2, 1 extra. So Pnx means n plus 1. Now the third space is R m by n matrix. M by n real matrix space. Okay, matrix of the order m by n. So for example 2 by 2 matrices basis is 1 0 0. Each number in each matrix 1. Okay, like this. So we are getting 4 matrix there. So this is the basis of the 2 by 2 matrices. Okay, 1 0 0 0, 0 1 0 0, 0 0 1 0, 0 0 0 1. So what will be the dimension here? Dimension is 2 multiply 2. That means 4. Okay, dimension of R2 by 2 is 2 multiply 2. That is 4. So dimension of m by n matrix means mn, m multiply n. Okay, so these are the some standard vector spaces and bases. Okay, standard basis of the vector spaces Rn, Pnx and Rm by n matrices. So this one just keep in your mind. Okay, now we will go to the some examples how to check the basis of the vector space. For example, the first one, examine whether the set B equal to x1, x2, x3 is a basis of R cube or not. R cube or not. So already we know R cube vector space dimension is 3. Standard basis already we know E1, E2, E3. Correct? So R cube vector space when we are taking the basis when we are checking, there is some rule we studied. Any set of more than n vectors is linearly dependent. It will not be a basis. That means already we know dimension of R cube is 3. That means R cube basis, how many vectors are there? 3 vectors are there. Correct? So what is the rule telling actually? Less than n vectors. That means less than 3 vectors in R cube, not a basis. Okay? And second rule when we are studied, any two bases of the vector space contain same vector, same number of vectors. So R cube, if any other basis when we are considering, it should have 3 vectors. Okay, it should have 3 vectors only, same number of vectors only. So 3 vectors only base is possible. Now what is the next one? That any linearly independent set containing n vectors is a basis of V. So if it is 3 for example, is it a basis or not? How we are checking? This should be linearly independent. So any linearly independent set containing n vectors, that means 3 vectors, should be a basis of V. Linearly independent condition it should satisfy. So here the dimension of R cube is 3, correct? And how many number of vectors, number of vectors in B actually, that is also 3. Number of vectors in the basis, there are 3. So these two numbers should be same. Okay, dimension of the vector space and the number of vectors in B should be same. If it is same, okay, only we need to check this set is linearly independent or not. If it is linearly independent, that will be a basis. Okay, so by using that rule, only we need to check whether the vectors in B are linearly independent or not. Okay, if it is linearly independent, that will be a basis, otherwise it will not be a basis. So linearly independent, for example, linearly independent, okay, what is the condition we are studied actually? Linearly independent checking, that means rank of A matrix equal to number of variables, correct? Number of variables. Otherwise, what we can check, determinant of A should be not equal to 0. So let me start this question here. Okay, linearly independent or not. So here just write the linear combination alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3 equal to 0, correct? As we discussed in the previous section, start from A matrix. A equal to, what is the matrix? First vector, write in row column wise 1 2 1, second vector column wise 2 1 0, third vector 1 minus 1 1, write in column wise like this. Now use the row transformation. First I am doing by row transformation, or you can check the determinant method also. Use the row transformation. First number should be 1 here. This number we are calling pivot number. So down numbers we need to change into 0 here, these two number. So what are the row transformation we are applying here? That is, the second row we need to change and the third row we need to change. So R2 plus is default, R3 plus is default. Opposite of 2 minus 2. Multiply pivot number coming on the first row. Opposite of 1 minus 1. Multiply R1. Correct? So equivalently you will get a matrix 1 2 1. First row no change. Now second row becomes 0 minus 3 and minus 3. Third row becomes 0 minus 2 and 0. Okay. Now again first number is 1. Now here second row starting number non-zero number should be 1. So second row we divide by minus 3 gives new second row. So equivalently the matrix you will get 1 2 1, you can get it 1 2 and 1. Okay, then 0 1 1 each number divided by minus 3 and 0 minus 2 0. So this number is the pivot number. Now pivot number coming on second row. Now pivot number, down number and top number we need to change into 0. So first row we need to change. So R1 plus default, opposite of 2 number minus 2, multiply pivot number coming on second row. Down number also we need to change. So R3 we need to change. R3 plus is default, opposite of minus 2 2, multiply pivot number coming second row. So by using calculator you can check it what is that transformed matrix. So matrix we will get 1 0 0 after calculation, 0 1 1 and the last row becomes 0 0 2 here. Now again this number we need to change into 1, that will be the next pivot number. So we need to divide R3 divided by 2 gives new R3. So equivalently the matrix 1 0 0 0 1 1 0 0 1, complete number divided by 2 here. Now this number is the pivot number, it is coming on third row. Now pivot number, top numbers we need to change into 0. So second row we need to change because first row number already it is 0. So R3 plus is, sorry, R2 we need to change. So R2 plus is default. Opposite of 1 minus 1, multiply pivot number coming on third row. So equivalently we will get equivalently matrix 1 0 0 and 0 1 0 0 0 and 1. So we will get fastly. Once we practice this transformation, we will get fastly. That will be easy. So now we can write what is rank of A. Rank of A, we are getting number of non-zero rows equal to 3, and rank of AB, sorry, number of variables equal to 3, alpha 1, alpha 2 and alpha 3, correct? So rank of A equal to number of variables, both are 3. Rank of A, it is same as the number of variables 3. So what we can say, the vectors are linearly independent. The vectors are linearly independent. So what we can say, B is a basis. B is a basis of R cube. Okay. So I hope you are clear. So R cube, same number of vectors means only we need to check linearly independent. Okay, once we get linearly independent, that will be a basis of that vector space. I hope you clear. Now other ways what we can do, you can just calculate the determinant of A. If you are getting determinant A not equal to 0, then also the same idea, basis will be, B will be a basis of that vector space. So instead of row transformation, you can do determinant A also should be not equal to 0 here. So I hope you clear here. Now we will go to the next section. So already I hope you clear how to check a vector space, a set of vectors basis or not using this condition. Only check here and you can verify that is basis or not. But if you are getting determinant A 0, that will not be a basis. Okay, determinant of A equal to 0. Okay, if you are getting not a basis. Or equivalently by using row transformation, rank of A, correct? If you are getting the rank of A less than, not equal to, or less than, okay, number of variables. Rank of A less than number of variables, we can say it is not a basis. Okay, or this one determinant. So both case it is linearly dependent. It is linearly dependent, so it is not a basis of that vector space. So I hope you are clear this one, how to check the basis or not. Okay, now we will do this example. Examine whether the set B equal to x1 1 comma 1 the vector, x2 equal to 3 comma 1 is a basis of R square or not. So as we know, here the vector space is R square, correct? So we know dimension of R square, that is equal to 2, correct? Now how many vectors are there in B set? The set B is, we have two vectors x1 and x2. So number of vectors in B is also equal to 2, correct? So we can say number of vectors in B equal to 2 and dimension of R square also equal to 2. So this set only we need to check that set is linearly independent or not. Okay, then if it is linearly independent, that should be a basis of that vector space R square. So we need to check B is linearly independent or not. Okay, linearly independent or not. If it is linearly independent, that set B is a basis, should be a basis of the vector space V. So for linearly independent case, we need to check the linear combination. take the linear combination alpha 1 x1 plus alpha 2 x2 equal to 0, correct? So alpha 1 multiply x1 is 1 comma 1 plus alpha 2 multiply x2 means 3 comma 1 equal to 0 means in r square 0 means 0 comma 0. Now when we are simplifying this one, we will get it alpha 1 plus 3 alpha 2 comma alpha 1 plus alpha 2, correct, equal to 0 comma 0. Okay, first number is first vector multiply with alpha 1, second vector multiply with alpha 2, after that add that two vector, we will get like this one. So just to take the first component alpha 1 plus 3 alpha 2 equal to 0, and second component alpha 1 plus alpha 2 equal to 0. So we are getting two equations here, alpha 1 plus 3 alpha 2 0, alpha 1 plus alpha 2 0. From here I want to calculate what is alpha 1 and alpha 2. Okay, so if all alpha 1 and alpha 2 0, that vectors x1 and x2 are linearly independent, correct? So for that, what we are doing, linearly independent or not, just calculate the rank of the matrix A, and it should be same as the number of unknowns or number of variables. So when we are starting that question, write the A matrix here, A equal to matrix, the first equation behind number alpha 1 behind number 1, alpha 2 behind number 3, and second equation 1 and 1. Okay, so this matrix actually you can write directly from the question itself. We can start from here. Actually these steps we can avoid. Directly we can go to the A matrix. A matrix means actually the first vector, that is 1 comma 1, we are writing like column wise. Second vector 3 and 1 we are writing like column wise. So we will get the same here. Okay, so we can start directly from the matrix A as I explained before. So A equal to 1, 3, 1 and 1. Now reduce this matrix into canonical form or row reduced echelon form, or you can reduce the echelon form also. So reduce and after that calculate the rank of the matrix. So first number here it is 1 already. Okay, first number is 1, that is the pivot number. It is coming on the first row here. So the pivot number down number should be 0. So we need to change the second row R2. So R2 plus is default. Opposite of 1 is minus 1. Multiply pivot number coming on the first row. So equivalently when we are using calculator, you will get a matrix into first row there is no change 1 3. Second row when we are using this transformation we will get 0 and minus 2. Now after that, so this number is 1 here, the pivot number, down number 0. Now second row first non-zero number should be 1. So we need to divide second row divided by minus 2 gives the new second row. So equivalently the matrix becomes first row same 1 3, second row complete number divided by minus 2. So 0 by minus 2 0, minus 2 by minus 2 that is 1. Okay, now this number is the pivot number now, correct? So pivot number coming on the second row. Now just pivot number, top number we are changing into 0. So we need to change the first row R1. So R1 plus is default. Opposite of 3 is minus 3. Multiply pivot number coming on the second row. So equivalently we will get a matrix. Okay, when we are changing using the calculator, you can do this transformation so that we will get the matrix. First row become 1 0 and 0 1. It is the second row. So now the matrix is in the canonical form or row reduced echelon form. So we can write what is the rank of the matrix A. Rank of the matrix A is, here it is 2, number of non-zero rows, that is 2, and here number of unknowns or number of variables, correct? Number of variables n equal to, how many variables we have? Alpha 1 and alpha 2. That means we have 2 here. So what we can conclude, actually rank of the matrix is same as the number of variables in our question, number of variables or number of unknowns. So we can say that two vectors are linearly independent, correct? That two vectors are linearly independent. So if it is linearly independent means, as I told you, the set B is a basis of R square. B is a basis of R square. So I hope you are clear this question how to do. If you are getting two vectors from R square, how we are checking that vectors are forming a basis or not. Just to check linearly independent or not. Okay, if it is linearly independent, it will be a basis. Otherwise, it is not a basis. Now the same way you can use the second method also, or just calculate the determinant of A here. Okay, determinant of A already here we are A already here we have A equal to 1 3 1 1, correct. So just calculate the determinant of the 2 by 2 matrix. So determinant of 1 3 1 and 1. So you know how to evaluate 2 by 2 determinant, just to cross multiply. Okay, 1 multiply 1 minus off diagonal multiply 1 multiply 3. 1 multiply 3. So when we are calculating 1 minus 3, 1 minus 3 means minus 2, correct. So it is not equal to 0. Determinant A not equal to 0. If 0 means linearly dependent, not equal to 0 means linearly independent. Linearly independent. So this method also you can use. Directly we are getting the answer. Determinant A is not equal to 0. So this set B is linear. Vectors are x1 and x2 are linearly independent. So the set B is a basis of the vector space R square, correct. So like this also we can do. Almost the calculation is same. There is no much difference. Okay. From here write the A matrix and check the using the row transformation you can check it is linearly independent or not, or using the determinant you can check it is it linearly independent or not. I hope you are clear this question. Now when I am coming to 1.7 section, linear mapping. Okay, linear mapping. So linear mapping or linear transformation you can see, or linear or vector space homomorphism. So let V and W be vector spaces over a field F. A function T from V to W. T from V to W is called a linear mapping. It should satisfy one condition. For all x, y belongs to V, and for every scalar alpha belongs to F, it should satisfy this condition. T of alpha x plus y equal to alpha multiply T of x plus T of y. Okay, or this first condition, second condition also okay. T of alpha x plus y equal to T of x plus T of y. T of alpha x equal to alpha multiply T of x. Or we can check T of alpha x plus beta y equal to alpha multiply T of x plus beta multiply T of y. Okay, now mostly we are questions we are using the second one. T of alpha x plus y equal to alpha multiply T of x plus T of y. You can see one example here. You can check it this one. Show that the mapping T from R square to R. R square to R. R square is the V and R is the W. So T from V to W is defined by T of U comma V equal to 3 times U minus 5 times V. Is a linear mapping, is a linear transformation, is our question. Okay. So T from R square to R. Okay. The first space is V, second space is W. So V is R square, W is R. So what we will do, if you are taking from here one vector R square means how it will come x and y or U and V, like that. Okay. For example, this question we are taken U and V. If we are taking one vector here U comma V, when we are taking transformation, it is equal to, it will come here. Here it is real number. Real number means single number, correct? So how it will calculate? 3 times U number minus 5 times V number. This is the transformation. Okay. For example, if I am taking one vector 1 and 2. So what is it? T of 1 and 2? T of 1 and 2 means 3 multiply U number and V number. U number is the first number, V number is the second number. So 3 times 1 minus 5 times 2. So 3 minus 10 minus 7. Okay, this number. So here it will be a single number because it is R, real numbers, correct? 1, 2, 3, 4, like that. But in the first set it is pair numbers, ordered pair, because it is R square, correct? So how it is transforming from one vector space to another vector space. One vector, how to transform to another vector, okay, in another vector space. That is what the transformation doing. Now what we need to do, this transformation, this mapping is a linear transformation or not, that is the question here. So we need to check this condition, t of alpha x plus y equal to alpha multiply t of x plus t of y. So for that what we will do, t of alpha x plus y equal to alpha multiply t of x plus t of y. So when you are doing question, actually this is the left hand side and this is the right hand side. Separately calculate left hand side and right hand side. Left hand side, how we are calculating? First calculate alpha x plus y. What is that? After that t of alpha x plus y. So we will get answer here. Right hand side, what we will do? Right hand side, first calculate t of x. Then calculate what is t of y. Then calculate alpha multiply t of x plus t of y. Okay, if you are getting both same, okay, left and right will be same. Left hand side equal to right hand side. So it will be a linear transformation. Okay, easy way you can think like this. So the question we have here, we did already that like that. See, first you calculated alpha x plus y. Take two vector x and y from the first set, okay, v set, okay, r square. After that calculate alpha x plus y like this. Then calculate what is t of alpha x plus y like this. Now right hand side, first calculate t of x, t of y, then alpha multiply t of x plus t of y. You will get like this one. So this one, whatever answer you are getting here, and it will be same as the answer here. So left and right will be same. It is a linear transformation, that mapping. So like that, any question we can do. You can check this one. You can practice here. Answer also here. Now we will go some questions from here. Before coming to the question, the ideas whatever we discussed in this section in brief I will given here. I was given here, so you can check it one by one what is given. For example, t from first vector space to another vector space. Okay, from the first vector space I am taken one vector x. Okay, it is as t of x. It is mapping to the second vector space y element, x going to y. So t of x equal to y. Okay, the transformation of the x vector under this mapping is equal to y. T of x equal to y. Okay, that is the meaning, t of x equal to y. Now we need to define, already remember kernel of t. What is the meaning? Kernel of t means set of all x belongs to v. The elements vectors from first set, that is mapping to 0 elements of the second set. For example, here 0 member is there, second set. So what are the elements? It is mapping to the 0 element of the second set. That is calling the kernel. What are the members here? Okay. So set of all x belongs to v. T of x should be equal to 0. 0 is a 0 vector in the second set. That is calling the kernel of the transformation. Now, what is the meaning of the range of t? Okay, range of the transformation, r of t, range. Okay, range of t, r of t equal to set of all y belongs to w. Range means from the second set vectors. So set of all y belongs to w such that t of x equal to y. That means transformation of x coming to that vector. That means what are the element transforming to this y. Okay, that is calling set of all y belongs to w, t of x equal to y. That means what are the image elements in the second set. So first set we are calling domain of the transformation. Second one we are calling codomain. And what are the ranges? Range element means what are the transformation coming to here, arrows are coming to here, which elements, that is calling the range. Okay, so y belongs to w, t of x equal to y, the transformation of x equal to y for all x belongs to v, that is calling range of t. Now dimension of kernel of t, that means kernel of t is a subspace. That subspace basis we are calling, basis dimension we are calling nullity of t, dimension of kernel of t, that means kernel of t basis, how many elements, that is calling nullity of t. And same way dimension of range of t basis having how many elements, that is calling rank of the transformation, r of t, rank of t. Okay, now what is the rule connecting rank and nullity is that rank t plus nullity t equal to dimension of the vector space. Rank T number plus nullity T equal to dimension of the vector, that vector space V, dimension of V. Okay, so that is the important rules, rule in the linear algebra. In the transformation, dimension of kernel of T, that is nullity T, dimension of range of T, it is calling rank of T plus nullity T equal to dimension of V here. Now, we will do one question from kernel. You can see, determine the kernel. Okay, determine the kernel of the linear transformation T from R cube to R cube defined by T of x, y, z equal to x minus y, y minus z and z minus x. Okay, so first try to understand the transformation T from R cube to R cube. Correct? So the first vector space we are calling V, second we are calling W. Okay, now kernel of T, before calculation, here transformation is defined. Here take a vector from R cube. R cube vector means should be 3 numbers x, y and z. Now when we are taking the transformation, it will go to the second set. Correct? How the answer transformation of second set? Here also R cube. So should have 3 numbers here. How we are getting that 3 numbers? First x minus y, first number. That means here x number minus y number. Second one y minus z. Third number z minus x number. For example, if you are taking 1, 2, 3 here. Okay, what is the transformation? It will come to the second set equal. Here first number x is 1, y number is 2, z number is 3. So x minus y. X minus y means 1 minus 2, minus 1. Y minus z, 2 minus 3, that is minus 1. Z minus x, 3 minus 1, that is 2. See, like this. I hope you clear how to coming the transformation. Now, what is we need to calculate? Determine the kernel of the transformation. Kernel. Kernel means, what is the meaning actually? We studied kernel means the set of the vectors in the first set. It should mapping to the second vector 0 element. 0, 0, 0. That means when you are calculating the transformation of x, y, z, here what answer you need to get it? 0, 0, 0. 0 element of the second set, W. Okay, that means here you can see many number will be there. For example, 1, 2, 3 or 4. Not 1, 2, 3, same 1, 0, something. Some vector here, x, y, z, different number when we are choosing, it will go to the 0, 0, 0. So what are that x, y, z? What are that vectors? That we need to calculate here. What are the vectors mapping to the 0 elements of the second set? For example, see, if I am giving here, okay, 1, 1, 1. What will be the transformation when we are applying here x minus y, y minus x, z minus x, all will be 0. Same way, 2, 2, 2, correct? It will go again 0, 3, 3, 3, it will go again 0. So, all numbers equal, it will go 0, 0, 0. So, what are that vectors here? How many vectors are here? That is meaning the kernel set. Okay. So, we will do one by one the kernel transformation, kernel of the linear transformation. We need to calculate what are the vectors mapping to the 0 vector of the second set. Okay, so let me start here. So kernel of T, already we know what is the rule. Kernel of T, ker T equal to set of all vectors. For example, I am taking U, x, y, z belongs to V, belongs to the first set, such that transformation of U should be the 0 vector of the second set, correct? 0 belongs to W. This is what the kernel of T. Now concentrate here, okay? Take a vector from the first set, then calculate this one T of U equal to 0, so that you will get it, the kernel, okay? So I am taking here one vector, x, y, z belongs to V, x, y, z belongs to V. So what happened actually? T of U, what will be the answer? 0, because it will map to the 0 element of the set. T of U equal to 0, correct? This is the kernel T rule. Transformation value equal to 0 here. Now, what is T of U? That means T of, what is U here? X, y, z equal to 0 means 0 vector of the second space. Here R cube is the second set. What is the 0 element? 0, 0, 0. Correct? Now that means what is t of xyz? It is given in our question here. X minus y, comma y minus z, comma z minus x equal to 0, comma 0, comma 0. Okay, now each number equal to 0. This vector equal to this vector means first number x minus y equal to 0, y minus z equal to 0, z minus x equal to 0. So you will get x equal to y here, y equal to z here, z equal to x here. So what is the meaning actually? X equal to y equal to z, correct? That means x equal to y equal to z. All the numbers should be same. Then that number mapping to that vector mapping to the 0 element of the second set. So how can we write kernel of t? Kernel of t equal to set of all x, y, z such that x equal to y equal to z. This is the kernel of the set. That means what is the meaning actually? That means kernel of t means what are the elements here? X, y, z will be same. So 1, 1, 1, 2, 2, 2, 3, 3, 3, like this members. This will be form the kernel of the transformation. Okay. So start with this condition, t of u equal to 0. U is the vector x, y, z. So t of x, y, z equal to 0. After that, just calculate x value, okay, y value and z value. Okay. So here any number x, y, z same. Any number you can select. Okay. Sometime we are getting the number itself. So this question, any number you can choose like that. So we will get kernel of t equal to x, y, z such that x equal to y equal to z here. I hope you clear. Now, when we are going to the second question, let t from r square to r square defined by, okay, t of xy is equal to x minus 2y, 3x plus 4y. Find the matrix of the transformation related to the basis b of r square, b of r square related to the basis b of r square. So this is very important idea. How can we represent the linear transformation by using matrices? Find the matrix of the transformation t related to the basis b of r square. So here this question, t from r square to r square, it is a linear operator. We are calling linear operator. Linear operator means the first space and second space both are same. Transformation from same space to same space, okay, itself. So here v, this is w, t from v to w, both are r square. Now transformation is given. Okay, transformation, what is the transformation in our question? That is x minus 2y, 3x plus 4y, the transformation. Okay, now here see, when we are doing this vector space basis is given. First b equal to x1 and x2. x1 means equal to 1 and minus 1. x2 equal to 2 and minus 3. Second vector space also same. So we can take basis b dash also the same vectors, x1 equal to 1 minus 1, x2 equal to 2 minus 3. If it is different, it will give different basis. Okay, here both are same. That means we are taken the same vectors. Okay, so instead of x1, x2, the second set we can write y1 and y2, so that you can easy to do other than same basis, because some here all are same, r square and r square. That's why same basis I am taken. If it is different, first basis we can take x1, x2, second vectors b dash, second basis b dash equal to y1 and y2. Now the transformation also defined. How the transformation is defined? T of x1, x2 or t of xy, t of x comma y equal to x minus 2y comma 3x plus 4y. Okay, now we need to represent this transformation by using matrix. That means from here we need to calculate what is the matrix of the transformation related to the basis b and b dash. B is here and b dash here. Okay, related to this basis, what is the matrix of that transformation. How can we represent that transformation using matrix? So we will come to this question we are doing. Okay, so first we are calculating the transformation T of, see here when we are, as I told you, see here, that is here T of x1 is there and T of x2. Calculate these two, T of x1, T of x2. First vector transformation, how it will go to the second, T of x2, how it will be. So I am going to calculate what is T of x1 equal to, because you know x1 is from the first set R square. So T of x1 means it will go to the second set R square, second vector space R square. So T of x1 always we can represent as the linear combination of vectors of the second set. That means alpha 1, what are the vectors, basis, second set basis y1 plus alpha 2 y2. Okay, x1 belongs to the first vector space. So T of x1 should be belongs to the second vector space, that is w. So what happened actually, T of x1 can be represented as the linear combination of the basis vectors of w. That means T of x1 we can write it as alpha 1 multiply the basis of this vector space b dash, that is alpha 1 y1 plus alpha 2 y2, like this. Okay, that is what we are doing here. After that, from that we are calculating what is the basis of, what is the matrix of the transformation. So we will start here. So T of x1, what is x1 here, 1 and minus 1, equal to alpha 1 multiply y1, what is y1, same 1 minus 1, because b and b dash we are taken same here, plus alpha 2 multiply y2, what is y2 here, that is 2 minus 3. Now simplify, we can use the calculator, we can check what is the values of alpha 1 and alpha 2. So here first we are doing what is T of x1 and 1. You know T of xy means what is given, x minus 2y, 3x plus 4y, correct? It is given in question. So T of 1 minus 1, what will be that one? Instead of x, 1, instead of y, minus 1. So here when we are substituting x minus 2y, x is 1, minus 2 times y is minus 1, comma 3 times x is 1 plus 4 times y is minus 1, like this. Okay, so when we are calculating equal to 1 minus of minus 2, correct? So 1 plus 2, that is 3, 3 multiply 1, that is 3, plus 4 multiply minus 1, minus 4, so 3 minus 4, it is minus 1. So here we are getting 3 and minus 1. I hope you are clear. Okay, now equal to alpha 1 multiply to inside, so 1 alpha 1, that is alpha 1, comma minus 1 alpha 1 plus alpha 2 multiply here inside, so 2 alpha 2 minus 3 alpha 2. Now add here, first numbers add, alpha 1 plus 2 alpha 2, comma minus alpha 1 plus minus 3 alpha 2, equal to 3 comma minus 1, left side same. Now equate, okay, two vectors are equal. So alpha 1 plus 2 alpha 2 equal to 3, minus alpha 1 minus 3 alpha 2 equal to minus 1. Now solve this equation, you will get what is alpha 1 and alpha 2. You can use the calculator also for you doing this one, or one of the solution method we can use. If you are using calculator, you can go to equation in the same calculator, and after that number 1, okay, an alpha an x plus bn y equal to cn. So just to give the behind number, first equation 1, 2 and 3, second equation minus 1, minus 3 and minus 1. Just apply the behind number. So immediately you will get the answer, alpha 1 equal to 7, alpha 2 equal to minus 2. Okay. Now same way calculate what is T of x2. Okay, so now I am going here, T of x2 vector equal to, T of x1 we calculated, now T of x2 equal to, okay. So how to write, take another two scalars, alpha 1 alpha 2 here we are used, so we can write alpha 3 multiply y1 plus alpha 4 multiply y2. Okay, because t of x2 also can be expressed as the linear combination of vectors of the basis of the second vector space. So y1 y2, so alpha 3 y1 alpha 4 y2, the same like this one. Okay, here alpha 1 alpha 2 we are used, here alpha 3 alpha 4, y1 y2 will be same. Now t of what is x2 actually? X2 means 2 minus 3 equal to alpha 3 multiply y1 means that is 1 minus 1 plus alpha 4 multiply y2 means 2 minus 3. Simplify same like previous one. 2 minus 3, what here it is, apply the linear transformation t of xy, this rule transformation, x minus 2y 3x plus 4y, correct? It is given in question. So t of 2 minus 3, when we are doing, x is 2, y is minus 3, so 2 minus 2 multiply minus 3 comma 3x, so 3 multiply 2 plus 4 multiply minus 3, correct? So when you are calculating how much you are getting, 2 minus 2 multiply minus 3 means plus 6, so first number will be 8 comma second number 3 multiply 2, that is 6, 4 multiply minus 3 minus 12, correct? So minus 6, 8 minus 6. Hope you are clear. So 8 comma minus 6 equal to, okay, the second part you can simplify same like here. So you will get alpha 3 plus 2 alpha 4 comma minus alpha 3 minus 3 alpha 4. Now equate that one. So alpha 3 plus 2 alpha 4 equal to 8 minus alpha 3 minus 3 alpha 4 equal to minus 6. Okay, so use the calculator for that again. Press the mode equation number 5, after that number 1, just apply the behind number, 1 equal to 2 equal to 8 equal to minus 1 equal to minus 3 equal to and minus 6 equal to. You will get the answer like alpha 3 equal to 12 and alpha 4 equal to minus 2. Okay, now once we go to this one, now we finished all. T of x1 we calculated, okay, and t of x2 also we calculated. Now we write the transformation matrix. Okay, so matrix of t related to the basis b and b dash equal to the matrix, the first two scalar number write in the column wise, 7 minus 2, then alpha 3 alpha 4 write in the column wise, 12 and minus 2. This is the matrix of the transformation, matrix of the linear transformation. I hope you are clear this one. Okay, so this point matrix of the transformation is important. Now another question, check whether the mapping T from R cube to R cube is defined by T of x, y, z equal to x plus 1 comma y comma z is a linear transformation or not. Okay, linear transformation or not. So actually for linear transformation what we need to check, T of alpha x plus y equal to alpha multiply T of x plus T of y. As I explained in the beginning, we need to check this one, we need to calculate this left hand side, we need to calculate this right hand side. If both are same, it is a linear transformation, otherwise it is not a linear transformation. And keep in your mind the transformation here, how it is like this transformation. T of, if you are taking a vector from R cube, for example 1, 2, 3, how it will go that one? The answer will be x plus 1, first number plus 1, so 1 plus 1, that is 2. Second number same, third number same, z is 2 and sorry y is 2, z is 3, both are same. Both are same here, so 2, 2, 3, okay, 2, 2, 3. So like this, first number only we need to add plus 1, second same, third same. Okay, so we will go to this is the transformation, we need to check linear or not. So we will start the question here t from r cube to r cube. So what we are doing from the first vector space, take two vectors x equals and y equals. For example, x equal to x1, x2, x3 because r cube. Y equal to y1, y2, y3. Okay. Now first what we need to calculate the left hand side. T of alpha x plus y. So first we need to calculate alpha x plus y equal to. Okay, so we are doing left hand side first. Alpha x plus y. So alpha multiply what is x? X1, x2, x3 plus y, that is y1, y2, y3. We studied how to add this one. First one multiply with alpha, alpha x1, alpha x2, alpha x3 plus y1, y2, y3. That means first add the first numbers alpha x1 plus y1, comma alpha x2 plus y2, comma alpha x3 plus y3. Now we need to do t of alpha x plus y. This is what the left hand side. T of alpha x plus y means t of this one, t of alpha x1 plus y1, comma alpha x2 plus y2, comma alpha x3 plus y3. Now how the transformation doing I told you. First number only adding 1, second and third same. That is the meaning t of transformation. So equal to what we will get, first alpha x1 plus y1 plus 1. Second same alpha x2 plus y2. Third same alpha x3 plus y3. So this is the left hand side. I hope you are clear. Now when we are going to the right hand side, RHS. RHS what we need to calculate in right hand side? Alpha multiply t of x plus t of y. Correct? So first we need to do what is t of x. T of x means t of x1, x2, x3. Correct? X means x1, x2, x3. So what we studied, t means first number we need to add 1, second number same, third number same. Now same way t of y. T of y equals t of what is y actually? y1, y2, y3. That means first number plus 1, y1 plus 1, y2 same, y3 same. Now when we are going, alpha multiply t of x plus t of y equal to, okay. So first one alpha multiply t of x already here, x1 plus 1, x2, x3 plus t of y means y1 plus 1, y2, y3. Now when we are adding these two, first vector we need to multiply with alpha plus second vector. So alpha multiplying time alpha x1 plus 1 multiply alpha, alpha, comma alpha x2, alpha x3. Every time we multiply with alpha plus y1 plus 1, comma y2, comma y3 same. Now we are adding the vectors, first numbers add, second numbers add, third numbers add. So alpha x1 plus alpha plus y1 plus 1. This is the first. Second one alpha x2 plus y2. Third one alpha x3 plus y3. So this is the right hand side. Now you can check it, left and right same or not. Okay, here first number alpha x1 plus alpha plus y1 plus 1. Here alpha x1 plus y1 plus 1. No, there is no alpha. It is not same. Right? So left hand side not same as the right hand side. So t is not a linear transformation. I hope you clear this question. We need to check like this separately. Okay, now let me go to one more question from here. From rank t plus nullity equal to dimension of v. From that rule, consider a linear transformation t from r cube to r. So keep in your mind The first vector space it is V, second vector space it is W, T from V to W is defined by T of x1, x2, x3 equal to 2x1 plus 3x2 minus x3 with dimension of kernel of T. Dimension of kernel of T equal to 2. It is already given. Find the rank of T. Rank of the transformation equal to what? This is the question. Okay, now think about this one. Dimension of kernel of T. Actually, what is dimension of kernel of T? We are studied here, correct? When I am given that flowchart, you remember dimension of kernel of T means nullity of T. Nullity, correct? Nullity, how much it is? 2. Dimension of kernel of T means nullity. Okay, we need to calculate what is rank of T. Okay, so actually what is the rule we studied? Rank of T plus nullity of T equal to dimension of the vector space. Okay, now in this question, rank T we don't know, we need to calculate, correct? Rank T. So I am writing rank T plus nullity T already given here, that is 2, equal to dimension of V. What is V here? R cube. What is dimension of R cube actually? Dimension of R cube, it is 3. We studied before, dimension of R cube is 3, the top number. Dimension of Rn is n, correct? So dimension of V means it is 3. Okay, dimension of the first vector space. Now from here easily we can calculate what is rank T, correct? So rank T equal to 3 plus 2 take to next side, 3 minus 2, so 1. So identifying the question is important, okay, so that you can do what is the rank of T. So I hope you are clear the first module. Okay, now I will start the second module. Module number 2, we have the following sections: 2.1 norms, 2.2 inner products, 2.3 lengths and distances, 2.4 angles and orthogonality, orthogonal basis, orthogonal complement. So we'll go one by one. First we have 2.1 norms. So norm of a vector space V is a function norm from V to R, x corresponding norm x, which assign each vector to its length. Norm of x means length of that vector. Okay, and it satisfies the following conditions: norm of lambda x equal to absolute of lambda multiply norm x, linearity property, and norm of x plus y less than or equal to norm x plus norm y, and norm of x greater than or equal to 0 for, and norm x equal to 0 if and only if x equal to 0. Now we will come to the questions. We need to calculate here L1 norm and L2 norm. So first question, compute the Manhattan norm or L1 norm of the following vectors: x equal to 1, minus 3 and 5. So as we discussed, Manhattan norm or L1 norm, norm of x, L1 norm equal to, we can do like a norm of modulus of x1 plus modulus of x2 plus modulus of x3, okay, or sigma I equal to 1 to n modulus of xi. So here the vector x equal to 1, minus 3, 5. So this is x1, x2, x3. So we can write absolute of 1 plus absolute of minus 3 plus absolute of 5. Okay, so we will get the answer 5 plus 3, 8, 8 plus 1, that is 9. Now compute the Euclidean norm or L2 norm of the following vectors. Euclidean norm means L2 norm, that is equal to root of x1 square plus x2 square plus x3 square, or we can write root of x transpose multiply x. Okay, so we will calculate this one equal to root of our vector here x equal to 1, minus 3, 5. So here x1, x2, x3. So 1 square plus minus 3 square plus 5 square. So equal to, we can get it the answer root of 5 square is 25, 25 plus 9 plus 1. So root 35. So this is just this module, this section only we have how to calculate L1 now and L2 now. Now we will go to the section number 2.2, inner product. Okay, so inner product, so V is a vector space over field F. Inner product of two vectors x and y is denoted by inner product xy and is defined as a scalar in F. Okay, so because it is calling scalar product, okay, satisfying the following condition: inner product xx greater than or equal to 0 and inner product xx equal to 0 if and only if x equal to 0. Inner product xy and inner product yx should be same, conjugate should be same, and inner product alpha x plus beta y z equal to alpha multiply inner product xz plus beta multiply inner product yz for all x, y, z belongs to V and alpha beta belongs to F. Now a vector space together with an inner product is calling inner product space. So after that, this section we studied positive definite matrix. Positive definite matrix means a real symmetric matrix. Symmetric matrix means A transpose equal to A is said to be a positive definite if inner product x Ax should be greater than 0 or x transpose Ax should be greater than 0, or we can say a matrix is positive definite if it is symmetric and all its pivots are positive in echelon form. Okay, or we can say if all upper k by k determinant of a symmetric matrix is positive, this matrix is a positive definite. Or other condition we can use, a matrix is positive definite, it is symmetric and all its eigenvalues are positive. Okay, now other one, if you have a 2 by 2 real symmetric matrix is a positive definite if and only if diagonal entries A and D are positive and the determinant A is positive. Okay, one of the conditions we can use. Now we have one questions here. Verify the following defines an inner product on R square or not. X equal to x1 x2, y equal to y1 y2 belongs to R square. Inner product xy is equal to x1 y1 minus x1 y2 minus x2 y1 plus x2 y2. Verify this is an inner product or not. We defined one inner product here, so we need to check all the conditions of inner product, it is satisfying or not. So first condition we studied, inner product x and x greater than or equal to 0 for all x belongs to the vector space V. Okay, inner product space V. This is the first condition, correct? So here we will check that one, what is inner product xx, this condition satisfying or not. So we have inner product xx equal, see already here we have inner product xy, this is inner product xy, x means x1 x2, y means y1 y2. Here we are taking x inner product. So how can we write that one? X1 multiply x1. Instead of y1 it will come x1 because both are x, minus x1 y2 means x2 minus x2 y1 means x1 plus x2 multiply y2 means x2, correct? So equal to x1 multiply x1 means x1 square minus x1 x2 minus x1 x2 minus 2 times x1 x2 plus x2 multiply x2 means x2 square. This means in simple way we can write x1 minus x2 whole square because using the rule a minus b whole square is a square minus 2ab plus b square, correct? So we can write x1 minus x2 whole square. This is always, it will be greater than or equal to 0 because it is square. Square of a number should be always greater than or equal to 0. So first condition is satisfied. Okay, inner product xx always it should be greater than or equal to 0. Now the same way inner product xx equal to 0 if and only if only x equal to 0, correct? So inner product value 0 only if x equal to 0. So we will check this condition now. So inner product xx equal to 0 means you will get x equal to 0 or not. That is the condition we need to check here. So inner product xx equal to 0 means, what is inner product xx? Just before we did x1 minus x2 whole square equal to 0. Okay, when you are simplifying this one, we need to get x equal to 0. That means x1 equal to 0, x2 equal to 0. We will check that one. So x1 minus x2 whole square. So delete this square. So it will come x1 minus x2 equal to root 0, that is 0. That means x1 equal to x2, correct? x1 equal to x2. That means x1 equal to x2 means we can have 1 1, x1 and x2 same, 2 2 same, 3 3, correct? This case only inner product is 0, correct? 0 0 also possible, but not only if x equal to 0. That means not always x equal to 0, correct? Not always x equal to 0, because 1 1 also, x1 equal to x2 only the condition, that is 1 1 also inner product value is 0, 2 2 also inner product value 0, 3 3 also 0. So not only at x equal to 0, but other points also there. What is our rule telling actually? Inner product xx 0 only if x equal to 0. Other cases it should not be 0. Okay, so but here other cases also it is 0. So the second condition not satisfied, this condition. Okay, so inner product xx equal to 0 if and only if x equal to 0, condition violating. So this one is not an inner product. I hope you clear. Now when we are coming to the next question, find the inner product xy, where x equal to 0 3 2, y equal to minus 2 5 and minus 3, using dot product as the inner product. So we will go this one. Inner product xy we need to calculate using dot product. Dot product means x dot y, correct? So how we are defining x dot y? If x equal to x1 x2 x3 and y equal to y1 y2 y3, then inner product xy means x dot y means x1 y1 x1 y1 plus x2 y2 plus x3 y3. That means x numbers multiply plus y numbers multiply plus z numbers multiply. So here for example it is equal to, what are the x numbers? The first vector is x1 x2 x3. Second one is y1 y2 y3. So x numbers multiply. What are the x numbers? 0 multiply minus 2 plus y numbers 3 multiply 5 plus z numbers 2 multiply minus 3. Immediately we will get answer. So 0 multiply minus 2 means 0, 3 multiply 5 means it is 15, 2 multiply minus 3 minus 6, so 9, correct? So this is the inner product x y. I hope you clear. Now the next one, check whether the following matrices are positive, definite or not. Check whether the following matrices are positive, definite or not. So positive, definite or not, just now we discussed the rule. First we need to check that matrix is symmetric or not. Okay, symmetric means A transpose should be same as A. So how can we check easily that one? Only check that one. Diagonal number, any number, no problem. Okay, but the other number, this number and this number should be same. Okay, this number and this number should be same. This and this should be same. So here already it is same. So it is symmetric, correct? Yeah, yes, it is symmetric. Now second one, we discussed this rule, we are using this one. Okay, if all upper k by k determinant of the symmetric matrix are positive, okay, all upper k by k determinant of upper k by k matrix is positive. So for example here when we are going this question, take the 1 by 1 upper left corner matrix, calculate the determinant. So determinant of 2, that is, you know already, it is equal to the same number. Determinant of a 1 by 1 matrix means it is same number. So it is greater than 0, it is positive, correct? Now the second one, upper corner 2 by 2, left corner 2 by 2 matrix we are taking. So determinant 2 minus 1 and 2. We can calculate, cross multiply, 2 multiply 2 minus 1 multiply minus 1. So it is 4 minus 1, that is 3, that also positive, greater than 0, correct? So second also satisfying. Now the third one, Third one means the 3 by 3 determinant. Okay, so we need to calculate determinant 2, minus 1, 0, minus 1, 2, minus 1, 0, minus 1 and 2, this determinant. So we will go for this calculation. Okay, so we will go to this calculation. Determinant of, okay, determinant of 2, minus 1, 0, minus 1, 2, minus 1, 0, minus 1 and 2. Already we studied how to calculate the determinant. So equal to first positive, then negative, then positive. Okay, take the first row for example. So first number is 2, second number minus 1, third number 0. Now first number is 2, delete the row and column. So write the remaining number, determinant 2 minus 1 minus 1 2. So determinant 2 minus 1 minus 1 2. Now minus 1 number coming row and column, delete, write the remaining minus 1 minus 1 0 2. So determinant minus 1 minus 1 0 2. Now 0 coming row and column, delete, so we will get minus 1 2 0 minus 1. Now calculate the determinant. So 2 multiply 2, cross multiply here, 4 minus 1 multiply minus 1, that is 1. Minus minus plus 1 multiply 1 minus 1 multiply 2 minus 2. Minus 0 multiply minus 1 0. Plus 0 multiply anything, it is 0. Minus 1 minus multiply minus 1 1 and 0. So we will get the answer 2 multiply 4 minus 1, that is 3. Okay, so 6 plus 1 multiply minus 2, that is minus 2. 6 minus 2, that is equal to 4. It is positive number, correct? So we are getting here this determinant also positive. So it is symmetric. The upper left corner 1 by 1 determinant positive, 2 by 2 determinant positive, 3 by 3 determinant positive. So that matrix is a positive definite matrix. Positive definite matrix. Hope you clear how to check this one. Okay, now we will do this question. Check whether the following matrices are positive definite or not. Check the following matrix is a positive definite or not. Okay, only one here, 4 minus 2 minus 2 and 3. So for positive definite matrix, okay, now we are doing this question. Check whether the matrix is a positive definite or not. Okay, 4 minus 2 and 3. So for positive definite, you remember what we need to do? First we need to check that matrix is symmetric or not, correct? Symmetric means, what is the meaning? A transpose should be same as A matrix. So how to check, already I told you. So here, you know, this number, any number, no problem, but this number and this number should be same here. So it is already same here. So yes, it is symmetric, correct? It is symmetric. This matrix is symmetric. So first condition is okay. Now we are going to the second condition. What is the second condition? The upper left corner k by k determinant should be positive, correct? So we need to calculate the determinant upper left corner k by k determinant. For example, first 1 by 1 determinant, that means determinant of 4 equal to, you know, determinant of a single number means the same number, and 4 it is greater than 0, it is a positive number. So first 1 by 1 determinant is a positive number. Now we are going to the 2 by 2 determinant. Okay, that means the determinant of 4 minus 2 and minus 3. Okay, so when we are calculating determinant, cross multiply, 4 multiply minus 3, main diagonal number multiply, minus off diagonal numbers multiply, minus 2 multiply minus 2. So 4 multiply minus 3 is minus 12, minus 2 multiply minus 2 means plus 2. So minus 12 minus 2 means minus 14, correct? Minus 14. But minus 14 is not a positive number. It is negative number, less than 0, correct? So this condition is wrong. All numbers should be positive numbers, greater than 0. First one condition is okay because it is symmetric. Second condition is okay because determinant is positive number. But third condition, less than 0, it is a negative number. It should be positive number, correct? So is it that matrix is a positive definite? No, it is not positive definite. Okay, so not positive definite. So I hope you are clear this question. Okay, how to check a matrix is positive definite or not. Now we will go to the 2.3 section, length and distances. Length and distances. So what are the idea this section? Briefly you can see, norm or length of a vector x belongs to V, norm x, it is calculated by using inner product as norm x equal to root of inner product xx. Norm x equal to root of inner product xx. So inner product either we can calculate by using dot product. Okay, this inner product xx, either you can calculate by dot product or whatever defined in the question. After that take the root of that one, root of inner product xx. Now if norm x equal to 1, that vector is calling a unit vector or normalized vector, norm number 1. Now if you want to make a vector normalizing, okay, it is calculating x cap equal to x divided by norm x, vector divided by norm of that vector, so that we can normalize that vector, so that the vector norm should be 1. Okay, how can we make the norm of that vector 1? That is normalized vector means x cap equal to x divided by norm x. Now there is one important inequality, Cauchy-Schwarz inequality. No, modulus of inner product xy less than or equal to norm x multiply norm y. Okay, we studied that one. Now norm or length of a vector using the dot product, the same rule whatever here discussed, norm x. Okay, writing separately, norm x equal to root of, if you are using dot product, root of x dot x. That means already we studied how to calculate the dot product, x dot x, x1 square plus x2 square plus up to xn square. Okay, for one example is given here, how to calculate easily. Now metric, okay, metric is the mapping D from V cross V to V cross V to R. That means if you are taking any vector x, y, x and y from V cross V, if you are taking a pair x, y corresponding to dxy, that means the distance of the vectors x and y. Now if it is calling a metric, it satisfies the following condition: always dxy greater than or equal to 0 for all xy belongs to V, and dxy equal to 0 if and only if x equal to y. dxy and dyx will be same for all xy belongs to V, symmetric condition, and dxz less than or equal to dxy plus dyz for all xyz belongs to V, triangle inequality. Now we are going to the questions here. Okay, so here before starting this question, we studied how to calculate the norm x, that means root of inner product x, correct? Now if you are using dot product as the inner product, it become root of x1 square plus x2 square plus x3 square, like that it is continuing. Okay, other case it will define from the question itself, so that we can calculate what is the inner product xx. Okay, now let me go to this question. Calculate the distance between the following vectors: x equal to 2, 3, 5, 1 and y equal to 2, 0, 9, 1. Calculate the distance between the two vectors. So we need to calculate the distance between x and y. Okay, we need to calculate the distance between x and y. That means we need to do norm of x minus y. We know how to calculate x minus y actually. X minus y means, x means 2, 3, 5, 1 minus y means 2 0 9 1. So we will get like x number subtract 2 minus 2, that is 0, 3 minus 0, that is 3, 5 minus 9 minus 4 and 1 minus 1, it is 0. Okay, so now you can apply here. So equal to norm of x minus y. Okay, so equal to root of, what is the rule actually, x minus y, x minus vector already here, norm of that vector. Okay, so here it is not mentioned which is the inner product. So if it is not mentioned, we can take dot product as the inner product. So what is the dot product actually? x1 square plus x2 square plus x3 square plus x4 square, like that it is continuing. So here x1 means the first number, x2 means the second number, x3 third number, and x4 is the fourth number, correct? So we can apply here root of 0 square plus x2 means 3 square plus x3 means minus 4 square plus x4 means 0 square. I hope you understood. So you can check the number in calculator, that is root of 3 square is 9 plus 4 square is 16. Okay, so root 25, so equal to 5. Equal to 5. So I hope you understood how to calculate the distance between two vectors. Okay, now we will come to this question. Suppose that x equal to 1 1 1. Find the length of x. Okay, length of x means norm of x. If the inner product which is different from dot product, it is not dot product, given by inner product xy equal to 4x1 y1 plus x2 y2 plus 4x3 y3. Okay, here x means you can take x1, x2, x3. Y means y1, y2, y3. It will give in the question anyway, y1, y2, y3. So we need to calculate norm of x, correct? Norm of x means, what is the rule actually? Root of inner product x. Now this inner product xx we need to calculate by using this defined way, inner product, correct? So equal to root of xx, here xy given, inner product xy given. So inner product xy, both we are taking xx. Okay, so how can we write that one? 4 multiply x1, instead of y1 we can give x1 because same, plus x2, y2 means same as x2, plus 4 x3, y3 means same as x3 because both vector same we are taken, x. Now just apply the number. So root of 4 times, what is the x1 number here in our question? x1 is 1, x2 is 1, x3 also 1. So 4 1 multiply 1 plus x2, that is 1, again x2 1 plus 4 multiply x3 is 1, again x3 is 1. So we will get to root of 4 multiply 1 means 4 plus 1 multiply 1 plus 4 multiply 1 means 1. So root of 9 we will get, 4 plus 4 8 plus 1 9, root 9, that is 3, correct? So answer equal to 3 here. Norm of x equal to 3. Hope you are clear this one. Now we will go to the next question. Suppose that x equal to 1 1 1. Find the length of x using the dot product as the inner product. Dot product as the inner product. Find the length of x. Length of x means we need to calculate norm of x using dot product as the inner product. Okay, norm x means actually inner product x and x. But inner product x means we need to take the dot product as the inner product, x dot x. So what was the rule actually? Root of x1 square plus x2 square plus x3 square, correct? x3 square. So equal to root of, what is x1 1 square plus x2 1 square plus x3 1 square, x1 x2 x3, that is our vector. So we can write root 3, that is the norm x. Hope you clear. Now we will go to the next one. Suppose that x equal to 1 by 2 minus 1 by 6 5 by 6 1 by 6. Find the length of x vector length, that means norm x, using the dot product as the inner product. Now one question is there, is it a unit vector? Okay, so unit vector means what happened? Unit vector means the norm x value you will get equal to 1. So we need to check that one. So first we will calculate norm x. Norm x means root of inner product xx, but we need to use the dot product. So root of x1 square plus x2 square plus x3 square plus x4 square. Okay, so equal to root of, okay, x1 means 1 by 2. Okay, so 1 divided by 2 square equal to 1 by 2 square plus minus 1 by 6 square minus 1 by 6 square plus x3 means 5 by 6 square plus x4 means 1 by 6 square. Okay, 5 by 6 square plus 1 by 6 square. So you will get, when you are calculating, equal to 1. Okay, so norm x equal to 1 we are getting. Now the question is it a unit vector? Yes, it is a unit vector, because norm x we are getting answer equal to 1. Norm x equal to 1 means it is a unit vector. I hope you clear this question. Now we will go to the next one. Verify Cauchy-Schwarz inequality for the vectors x equal to minus 2 3 1 and y equal to 3 minus 4 and minus 1 in R cube. Verify Cauchy-Schwarz inequality. Okay, already we studied what is the Cauchy-Schwarz inequality. That is modulus of inner product xy less than or equal to norm x multiply norm y. Correct? So we need to check here. So we need to calculate what is inner product xy, norm x, norm y separately. For example, inner product xy first. Okay, here it is not mentioned which one we are using as inner product. So we can take dot product as the inner product. Okay, if we are not mentioning, we can take dot product as the inner product. So inner product xy equal to, what was the rule actually? X numbers multiply plus y numbers multiply plus z numbers multiply. So x1 x2 plus y1 y2, sorry, we can take first the first vector x1 x2 x3, second vector y1 y2 y3. So x numbers multiply means x1 y1 plus y numbers multiply means x2 y2 plus z numbers x3 y3. Okay, or we can write directly x numbers minus 2 multiply 3 plus y numbers 3 multiply minus 4 plus z numbers 1 multiply minus 1. Okay, minus 2 multiply minus 3, that is minus 6, plus 3 multiply minus 4, that is minus 12, then 1 multiply minus 1 minus 1. So we will get minus 19. Okay, now norm x equal to dot product means root of x1 square plus x2 square plus x3 square. That means root of what is x1 minus 2 square plus 3 square plus 1 square. That means root of 2 square means minus 2 square means 4, 3 square is 9 plus 1 square is 1, so root 14. Now norm y equal to the same rule, root of y1 square plus y2 square plus y3 square. So 3 square plus minus 4 square plus minus 1 square. So 3 square is 9 plus 4 square is 16 plus 1 minus 1 square is 1. So root 26. Now apply that number here in our question. So modulus of inner product xy is minus 19 less than or equal to norm x. Norm x means root 14. Norm y means root 26. Absolute of root 19 means minus 19 means you can delete minus sign. So 19 less than or equal to root 14 multiply root 26. You can calculate. You will get approximately 19.08 something. So the Cauchy-Schwarz inequality is verified here because this is small number, this is the bigger number, correct? Bigger number or equal also okay. So Cauchy-Schwarz inequality is verified. Verify means left and right this inequality hold or not, less than or equal to, here small, here bigger, or equal, both are same. So here it is correct. So verified. Hope you clear. Now when we are going to 2.4 section, angle and orthogonality. So we studied the angle between two vectors. Okay, how to calculate? Theta equal to cos inverse inner product xy divided by norm x norm y. Okay, can memorize that one. And we studied the orthogonal and orthonormal vectors. Okay, here it is mentioned. Two vectors x and y inner product space we call orthogonal means inner product will be 0. Orthonormal means in additionally one more property satisfy. If norm x equal to norm y equal to 1 means normalized vector, correct? So if it is orthogonal and normal, orthogonal and norm 1 means orthonormal. Now the same idea we are extending to a set. A set of vectors is orthogonal means every vectors is orthogonal to every other vectors in S. Same way orthonormal means a set is orthonormal set means every vectors are orthogonal to each other and each vectors normalized vector. Norm should be 1. Now if a matrix is orthogonal matrix, A multiply A transpose, always we are getting the identity matrix. Okay, so these ideas you can just revise. One is orthogonal. Orthogonal means inner product xy should be 0. Now if one more condition satisfy, norm x equal to norm y equal to 1 means this is calling orthonormal. Orthogonal plus normal, that is orthonormal. Okay, that means both conditions. Okay, orthogonal and orthonormal. This condition only normalized. Normalized means norm should be 1. So orthonormal means what is the condition? It should be orthogonal and it should be normalized. Normalized vector, that is norm should be equal to 1. Now when we are coming to here some examples, prove that the square matrix is orthogonal. Prove that the square matrix is orthogonal, correct? So what we need to do, this matrix is orthogonal means we need to check A multiply A transpose equal to identity matrix or not. I means what is that matrix? Identity matrix 1 0 0 1. So we will check here A multiply A transpose equal to, what is A matrix? 0 1 minus 1 0. Multiply A transpose matrix. A transpose means A matrix first row write it as first column 0 1, second row write it as second column. Now multiply these two matrices. Okay, we studied how to multiply two matrices. Okay, we need to multiply like first row with the first column, first row with the second column, second row with the first column, second row with the second column. It is 2 by 2. So we can do here equal to the matrix. First you can do R1 C1. First matrix we are taking rows R1 R2. Second matrix we are taking columns. C1, C2. So first row, this is the first row, 0, 1. Multiply with the first column, 0, 1. So you can multiply like first number with first number, 0 multiply 0, plus second number with the second number, 1 multiply 1. So you will get 1. So the first number is 1 here, R1, C1. Now if you want R1, C2, first row, 0, 1, multiply second column, minus 1, 0, correct? This is the second column, minus 1, 0. So again first number with first number, 0 multiply minus 1, plus second number with second number, 1 multiply 0. So you will get answer is 0. So second number here 0. Similar way, second row with column 1. Second row is this one, minus 1 with 0. So R2 C1 equal to minus 1 0 multiply column number 1 0 1. So first number with first number, minus 1 plus multiply 0, plus second number with the second number, 0 multiply 1, that is 0. So here 0. Now same way you can do R2 C2. R2 means minus 1 0, C2 means minus 1 0. When we are multiplying, you will get 1. So 1 0 0 1. So it is same as the identity matrix, correct? So A multiply A transpose equal to I matrix. So this matrix is orthogonal. So that means A is orthogonal. I hope you are clear how to check a matrix is orthogonal or not. Okay, now we will come to the next one. Find the angle between the following vectors. Find the angle between the following vectors and check whether they are orthogonal or not. Okay, we need to find the angle between these two vectors and check whether they are orthogonal or not. So x vector is 1, 2 and minus 3, y vector is 1, minus 4 and 3. Okay, here use the dot product as the inner product. Orthogonal means what is the meaning? Inner product will be 0, correct? Or angle will be 90 degree. So we can go here, for example, find the angle between the following vectors means rule is theta equal to cosine inverse inner product xy divided by norm x multiply norm y. So we will calculate separately what is inner product xy using the dot product. So x numbers multiply, y numbers multiply, z numbers multiply. So x numbers are 1 multiply 1 plus y numbers 2 multiply minus 4 plus z numbers minus 3 multiply 3. So you will get 1 multiply 1 1, 2 multiply minus 4, that is minus 8, and minus 3 multiply 3 minus 9, so minus 16. Now norm x dot product, what is the rule? Root of x1 square plus x2 square plus x3 square. That means root of first vector 1 square plus 2 square plus minus 3 square. That means we will get root of 9 plus 4, that is 13, 13 plus 1 14, root 14. Now norm y, same rule, root of y1 square, 1 square plus minus 4 square plus 3 square equal to 9 plus 16 plus 1 root 26. Now you can apply here cosine inverse inner product xy means minus 16 divided by norm x root 14, norm y root 26. So you can check the answer from calculator. You will get 146.99 degree if you are using degree measurement, or 2.57 approximately as the radian measurement, correct? So this is the angle between the two vectors. Now it is a question whether they are orthogonal or not. Is it orthogonal? No, not orthogonal. Why not orthogonal? Because inner product xy not 0, correct? It is minus 16 here. If inner product xy 0, it is orthogonal, or theta is not equal to 90 degree. If theta 90 degree also orthogonal, correct? So here both are not say correct. Inner product xy is not 0, so it is not orthogonal, or angle not 90 degree, it is not orthogonal. I hope you clear this question. Now the second one. Verify the set of vectors E1, E2, E3 form an orthonormal set. Form an orthonormal set. Orthonormal means it should be orthogonal and it should be normalized. Normalized vector. All vectors should be normalized vector. That means norm should be 1 for all vectors. Norm E1, norm E2, correct, and norm E3. All should be 1. And orthogonal means each pair of vectors E1, E2, E1, E2, E2, E3, E1, E3 all should be 0. Inner product value should be equal to 0. So we will check one by one. First we will check inner product. Inner product E1, E2. First we will check it. Then inner product E2, E3 we can check it. Then inner product E1, E3 we can check it. Each pair of vectors inner product value should be 0. After that we need to check what is norm E1, norm of E1, norm of E2 and norm of E3. All should be 1 here. So first inner product E1, E2. Take the dot product as the inner product. It is not mentioned in the question. So if it is not mentioned, you can take the dot product as the inner product. So for example here E1 multiply E1 E2 inner product. So x numbers multiply 1 multiply 0 plus y numbers 0 multiply 1 plus z numbers 0 multiply 0. Answer will be 0. Now E2 and E3 inner product. Multiply the x numbers E2 and E3. 0 multiply 0 plus 1 multiply 0 plus 0 multiply 1. So this also 0. Now E1 and E3. 1 multiply 0 plus 0 multiply 0 plus 0 multiply 1. That also 0. So all inner products are 0. So orthogonal, correct? It is orthogonal set. The set E1, E2, E3 are orthogonal set. Now norm E1. Norm E1 means root of, correct? Root of x1 square, that is 1 square plus x2 square means 0 square plus x3 square 0 square. It is 1. Norm of E2 same 0 square plus 1 square plus 0 square. This is also 1. Norm of E3 root of 0 square plus 0 square plus 1 square, that also 1. So normalized vector, correct? Normalized vector. All are normalized vector. That means all norm is 1. So what we can say? The set S is an orthonormal basis. Orthonormal set. Orthonormal set. Hope you clear how to check orthonormal or not. Now next question. If the vectors x equal to 1 1 k and y equal to 1 minus 4 3 are orthogonal, then find the value of k. These two vectors are orthogonal, already given. Orthogonal means what is the meaning? Inner product xy equal to 0. What is the value of k? Okay. So inner product xy equal to 0 means using dot product. It is not mentioned here. So we can take dot product as the inner product. So what is the dot product as the inner product? X numbers multiply 1 multiply 1. Y numbers multiply 1 multiply minus 4. Z numbers k multiply 3 equal to 0. That means 1 multiply 1 1 minus 4 multiply 1 minus 4. K multiply 3 3k equal to 0. That means 3k equal to, you can simplify first. 1 minus 4 means minus 3 plus 3k equal to 0. So 3k equal to minus 3 take to next side become 3. So means k equal to 1 here. Can divide both sides by 3. You will get k equal to 1. So this is what our question. If the vectors x and y are orthogonal, find the value of k. So which value of k that two vectors are orthogonal? K equal to 1. Now the next one. Find the values of x, y and z if the given matrix A is orthogonal. This matrix is orthogonal. What will be the values of x, y and z? That is the question here. If these two vectors are orthogonal, what are the values of x, y and z? So we will do this question. Already we studied what is the meaning of orthogonal matrix. Orthogonal matrix means what condition it should satisfy? A multiply A transpose equal to I. Correct? Now what is the A matrix here? A matrix is x 0 0, y z 0, correct, and 0 0 1. Multiply A transpose. What is A transpose? First row, write it as first column. Second row, write it as second column. Third row, write it as third column. Equal to I matrix, correct? That is 1 0 0 0 1 0 0 0 1, because it is 3 by 3 matrix, identity matrix. Okay. Now the left side we need to simplify here. This one, you know how to multiply two matrices. So when I am multiplying, I will write here the final matrix. You can check it. So first row multiply with the first column. Okay, this is rows R1, R2, R3, column 1, column 2, column 3. So what we need to do first? R1 C1, R1 C2, R1 C3. Okay, full 3 by 3 matrix we need to calculate. Then R2 C1, R2 C2, R2 C3, R3 C1, R3 C2, R3 C3. These 9 numbers we need to calculate separately. So for example, this question R1 C1, that means x multiply x square, plus 0 multiply 0, 0 multiply 0 is 0. So only x square. Now first row with second column. So x multiply y, xy, plus 0 multiply z, 0 multiply 0, 0. Now R1 multiply C3. So x multiply 0, 0, 0 multiply 0, 0, 0 multiply 1, 0. Same like you can continue. Here you will get yx. Here you will get y square plus z square. And here you will get 0. Last row 0, 0 and 1. Equal to matrix 1 0 0 0 1 0 0 0 1. Now when we are doing this matrix equal to this matrix, that means first number equal to the first number. So x square equal to 1. Second number equal to second number, that means xy equal to 0. xy equal to 0. Third number equal to third, 0 equal to 0, correct. Fourth number equal to 0, yx equal to 0. Already we wrote that one, xy equal to 0. Now this number y square plus z square equal to 1. Y square plus z square equal to 1. Now other numbers are same. Here 0, here also 0. 0, 0, 1. 0, 0 and 1. So other numbers we are getting the same numbers. Okay, now just to simplify, calculate x, y and z. For example, here x equal to plus or minus root 1, that is plus or minus 1. So just apply the numbers in the x number here. First x equal to plus 1, you will get to what is the y number. For example, here x equal to 1 is there, x equal to minus 1 is there. Now x equal to 1, from here calculate what is the y number, y equal to 0. If x equal to minus 1 also, y equal to 0. Now here calculate z number from here, correct. Y is 0 in both cases. So 0 plus z square equal to 1. So z square equal to 1, z equal to plus or minus 1. Okay. That means what are the numbers? Z numbers, z equal to plus 1, z equal to minus 1. So these are the values of x, y and z. I hope you are clear. this question. Now we will go to the next one. Find the values of x and y if the given matrix A is orthogonal. Find the values of x and y if the given matrix is orthogonal. So orthogonal matrix, correct? Orthogonal means, what is the meaning? A multiply A transpose equal to identity matrix. So A matrix is minus x 0 0 y. Multiply A transpose matrix. What is A transpose? First row, write it as first column. Second row, write it as second column. When we are multiplying, we will get answer I 1 0 0 1. Identity matrix order 2 by 2. Now from here we need to calculate what is x and what is y. Correct? So multiply these two matrices. Okay. First row multiply with the first column. Okay, so we will get the answer here. You can check the multiply. We will get the matrix like x multiply minus x, x square. Here x square will get it, 0 will get it, 0 y square. You can check it all the multiplication first r1 c1, r1 c2, r2 c1, r2 c2. Okay, we studied the matrix multiplication before. So equal to 1 0 0 1. Now calculate x and y. First number should be same as the first number. So x square equal to 1. So x equal to plus or minus root 1. That means plus or minus 1. And here y square equal to 1. So y equal to plus or minus root 1. That is plus or minus 1. So what are the values of x and y? X equal to plus or minus 1, y equal to plus or minus 1. So that is the answer here. Hope you clear. Now we will go to 2.5 section. 2.5 section we are studying orthogonal basis and orthonormal basis. Okay. So what are the conditions here? We can write orthogonal basis. And we need to study orthonormal basis. Okay, that means if we are getting a set of vectors b equal to x1 x2 like that, for example b equal to x1 x2 and x3, I am taking three vectors here. Okay, when we are telling this set of vectors are orthogonal basis, when we are telling this set of vectors are orthonormal basis, okay, what are the condition it should satisfy? The first condition, orthogonal basis, for example, it should be a basis, that b should be a basis. Second condition, it should be orthogonal. Orthogonal, okay, orthogonal means when we are calculating inner product x1 x2 and inner product x2 x3 and inner product x1 x3, each pair inner product, all should be, value should be 0, correct? So orthogonal and basis means orthogonal basis. Now what are the conditions for orthonormal? Firstly, it should be a basis of the vector space. Second one, it should be orthogonal. Orthogonal means, as I told you, inner product x1 x2 should be 0, inner product x2 x3 should be 0, inner product x1 x3 should be 0. Now third one, it should be normalized vector. All should be normalized vector. That means a unit vector. That is the meaning normal, orthonormal basis. Okay. Orthonormalized means norm x1 equal to norm x2 equal to norm x3 equal to 1. It should be 1. So these three conditions are satisfied means it is calling orthonormal basis. Okay, these two conditions are satisfied means orthogonal basis. Already we studied the basis. What is the meaning of basis in before section? We discussed and we did many questions from this one, basis. So when I am doing question from here, I will not check the basis condition. You can study before we discussed that one, basis. Okay, so let me go to one question. For example, this question, show that the basis b equal to 1 2 1 1, 2, 1, 2, 1 minus 4, 3 minus 2, 1 of R cube is an orthogonal basis. Okay, is an orthogonal basis. This is what we need to check. Use the dot product as the inner product. So orthogonal basis. So it should be a basis and it should be orthogonal. These two conditions we need to check here. So basis condition already given in the question. See, show that the basis. So this is already basis. Okay, these three vectors forming a basis already it is given. If it is not given as a basis, okay, whatever we studied in 1.5 and 1.6, it will be the basis. How to check? How we are checking? Just checking linearly independent or not. Correct? Linearly independent or not. That means what we are doing for linearly independent or not. Either you can do the rank of A should be equal to number of variables, or we can check determinant of A should be not equal to 0. One of the condition, this video, same video we are discussed in the before, or we can use the recorded class basis and linear independent dependence, that one. So this question I am not checking this condition because it is already given, it is a basis. So basis condition already it is satisfied. Only we need to check this set is an orthogonal set or not. Okay, this set is an orthogonal set or not. So what we are doing, we need to calculate what is inner product xy, we need to calculate what is inner product yz, and we need to calculate what is inner product xz. Each pair of the vectors inner product calculate, it should be 0. So for example xy, dot product is the inner product. So we can do x numbers multiply 1 multiply 2 plus y numbers multiply 2 multiply 1 plus z numbers 1 multiply minus 4. You will get answer equal to 0. Now same y and z x numbers 2 multiply 3, y numbers 1 and minus 2 plus z numbers minus 4 multiply 1. So you will get this also 0. Now x and z, first and last vector, x numbers 1 multiply 3 plus y numbers 2 multiply minus 2 plus z numbers 1 multiply 1. So this is also equal to 0. So inner product is 0. So it is an orthogonal set. Correct? It is an orthogonal set. So orthogonal plus basis means what we are calling orthogonal basis. Calling orthogonal basis. I hope you clear this question. Now if you want to check the orthonormal basis, for example here it is only checking orthogonal. Now if you want orthonormal means one more condition extra we need to check that one. Correct? Basis already we have, and orthogonal set already we checked it. Third one we need to check normalized or not, normalized vector or not. So normalized vector means what we do, norm x1, x calculate, norm y calculate, norm z calculate. Okay, so if you are getting one all, it is orthonormal basis, otherwise not. Okay, so for example here when we are doing root of, okay, what is x actually? 1 2 1, correct? So 1 square plus 2 square plus 1 square. So here itself it is equal to root of 4 plus 5 plus 6, root 6. It is not same as 1. Okay, so here itself we can generalize that one. It is not an orthonormal basis because norm is not 1. Here also root y also, inner product norm y also you can calculate. Norm y means 2 1 minus 4 vector. So 2 square plus 1 square plus minus 4 square. It is not equal to 1. It is clear. And third one, 3 minus 2 1. So root of 3 square plus minus 2 square plus 1 square. This is also not same as 1. So it is not an orthonormal basis here. Hope you clear this one. So this section 2.5 section only we are studying this one, how to check the orthogonal basis and orthonormal basis. Now we will go to the 2.6 section, orthogonal complement. Okay, orthogonal complement. So orthogonal complement we are representing by using perp, W perp symbol. W is a subset. Okay, that subset is a subspace. W is a subset of an inner product space V. The orthogonal complement of W is denoted by W perp. W perp, it consists of W perp equal to set of all V belongs to V such that inner product VW equal to 0 for every W belongs to W. So this W perp is always a subspace. We discussed that one. So we will do one question, how to calculate the W perp. Set of all V belongs to V such that inner product VW should be 0. Okay, so we will go to one question. Example. Find W perp. Suppose that W equal to 1, 7, 2 vector and minus 2, 3, 1 is a subspace of R cube. Is a subspace of R cube. So we will go to this question, how to do the W perp. Already we know this set W perp, set of all V belongs to V such that inner product VW equal to 0 for every W belongs to W. So for example here in our question here, W means we have two vectors here, correct? In W we have two vectors. For example, the first vector I am just taking as U and second vector as W. For example, U equal to 1, 7, 2. Small letter W equal to minus 2, 3, 1. The second one. Okay, now what is the W perp actually? W perp means set of all V belongs to V such that set of all vectors in the vector space such that this inner product V with all vectors of W should be 0. Okay, so we can write like this. For example, V W equal to 0 for all W belongs to W. So very simply we can do, for example, if you want to calculate W perp, we need to calculate V belongs to V. It should be a vector in V, correct? So I am taking just one vector from V. What is V over here? R cube. Here our vector space is R cube. So take a one vector from here. For example, I am taking V equal to R cube means we have X, Y, Z. Three vectors will be there, correct? Belongs to R cube. I am taken from vector space one vector. From V I am taken one vector, that is V equal to X, Y, Z. Now what is the condition telling? Vector V with every vector in W, answer should be 0. That means, for example, vector V with U, inner product will be 0. Vector V with second vector W, inner product will be 0. Okay, we are taking one vector from the vector space and this vector with all the vector from W. Okay, inner product should be 0. That means VU and VW, correct? These both inner product value should be equal to 0 here. I hope you understood that one. Okay, here this is U, this is W. So inner product with U and inner product with W both should be 0. Now from this we need to calculate what is this vector. What are these vectors? X, Y, Z. Okay, so we will go to the question. For example, inner product inner product VU equal to 0. Okay, calculate the inner product V and U. V means X, Y, Z. U means 1, 7, 2. So calculate the inner product. Use the dot product as the inner product. So how we will get that one? V and U. Okay, inner product. So X multiply 1, that is X. Plus Y multiply 7, that is 7Y. Plus Z multiply 2, that is 2Z. Equal to 0. Now second one, inner product V and W. V means X, Y, Z. W means minus 2, 3, 1. Take the inner product, that means the dot product. X multiply minus 2, minus 2x. Plus 3 multiply Y, 3Y. Plus 1 multiply Z, Z. Equal to 0 here. From this you need to calculate what is the X value and what is the Y value. What are the Z values. Okay, X, Y and Z we need to calculate from here. So we need to solve this system. Okay, so we studied how to solve a system of equation in 1.3 section. So we will go that one. So write the AB matrix. AB matrix. Okay, so AB equal to first equation. What is the first equation? X plus 7y plus 2z equal to 0. Write like a matrix. So 1, 7, 2 and 0. Correct? 1, 7, 2 and 0. Second one, minus 2, 3, 1 and 0. Minus 2, 3, 1 and 0. Okay. Now, if you are not considering these steps, you can write directly from here also. See, our vectors are 1, 7, 2 and minus 2, 3 and 1. Correct? So, you can go from here directly this A, B step. A and B. How we are writing? First to see this vector, first vector, write it as first row, 1, 7, 2. Second vector, second row, minus 2, 3 and 1. Right side always it will be 0 because orthogonal, inner product equal to 0. So here will be 0, 0 and 0. So this is the easier way to write directly AB so that you can avoid these steps. Okay, you can reduce the timing. So AB equal to, okay, this is the matrix. Now this matrix just change into the canonical form. Already we know using the row transformation. So how we are doing? First number should be 1. That number is the pivot number. Now pivot number coming on first row. Down number we need to change into 0. Correct? So second row we need to change. So R2 plus is default. Opposite of minus 2, 2. Multiply pivot number coming row, first row. So equivalently this matrix becomes 1, 7, 2, 0. Second row using that transformation you will get 0, 17, 5 and 0. Now after that what we will do? This one next row, second row, first non-zero number should be 1. So second row divided by 17 gives new second row. So equivalently the matrix 1, 7, 2 and 0, 0, 1, 5 by 17 and 0. Each number divided by 17, correct? Now this is the pivot number. Pivot number coming on second row now. Now pivot number, top number it should be 0. So R1 we need to change. R1 plus is default. Opposite of 7 minus 7. Multiply the pivot row, second row. So equivalently the matrix becomes, okay, the first row becomes 1, 0, minus 1 by 17 and 0. Second row 0, 1, 5 by 17 and 0. So now we are getting the matrix in canonical form. So now you can check what is the rank of A and rank of AB. Both are same, correct? So it is consistent. Always it will be consistent because it is a homogeneous system. But anyway, rank of AB is same as rank of A is 2. Now rank of A equal to 2 we are getting. Number of variables. How many variables we need to calculate? There are 3. X, Y and Z. Here it is mentioned, correct? X, Y and Z. We have 3 variables. So rank of A less than number of variables. So that means infinitely many solutions. Infinitely many solutions. So I hope you clear. We started with the AB matrix here. We need to calculate X, Y, Z. Already this system is consistent because it is homogeneous system. Right side is 0. Okay, it is consistent, but only we need to check how many solutions, infinitely many solutions are there, because here rank of A less than number of variables. So what we are doing, this matrix we are converting into equation again. 1, 0, minus 1 by 17 and 0, 0, 1, 5 by 17. First number stand for X number, second is Y, third for Z and right side number. So first row become 1 multiply X, X. Okay, so I can go 1 multiply X means X, minus 1 by 17 multiply z equal to 0. And second one, y multiply 1 y plus 5 by 17 z equal to 0. Correct? Equal to 0. And here number of variables is 3. Rank is 2. So 3 minus 2 equal to 1. One free variable will be there. Correct? One free variable. You can take z equal to free variable, z equal to k1, any number we are substituting. So here we can write this as z equal to k1. So how to write this first equation? X equal to 1 by 17, z means k1. From here y equal to minus 5 by 17 k1 and z equal to k1. I hope you clear. Now here for convenient we are taking just k1, choose k1 equal to just 17. Okay, because divided by 17 you can eliminate here. So I am just taking k1 equal to 17 here. So how we are taking x equal to 1, because this 17 will cancel. Y equal to minus 5 and z equal to 17. Okay, so we can write the w perp as the orthogonal complement. W perp equal to the span of the vectors, okay, 1 comma minus 5 comma 17. Okay, 1 minus 5 or 17. So this is the w perp, orthogonal complement of w, span of 1 minus 5 and 17. Or you can write like the span of the vectors, span of the vector. Okay, see k1, if you are not taken 17, you can write like here, see k1 behind number 1 by 17, comma here k1 behind number 5 minus 5 by 17, and here k1 behind number, that is 1. This is also correct here. So this is the point in this section, only how to calculate the orthogonal complement. So I hope all are clear from 1.1 to 2.6. Okay, you can practice more questions for more understanding. This is just one worksheet only. Okay, we are solved a little fastly. So thank you for watching this video. Thank you very much.